Part 1. The stillness that was never real. Close your eyes for a moment and think about where you are right now. Maybe you are lying in bed with the lights off. Maybe you are sitting in a chair with something warm to drink, the room quiet around you, the only sound coming from somewhere outside or from the ambient hum of whatever building you are in. Everything within your immediate physical world is still. The walls are not moving. The floor beneath you is solid and motionless. The ceiling has not shifted since you last looked at it. The air is simply existing, doing nothing dramatic, going nowhere in particular, and every single piece of that feeling is wrong, not slightly wrong. Not wrong in some minor, pedantic, philosophical sense that physicists argue about in the footnotes of papers. Wrong in the most direct and fundamental way possible. Right now, as you absorb these words, your body is hurtling through space at a combined velocity that makes the fastest aircraft ever designed look like it is crawling in place. You are not at rest. You have never been at rest. There is no rest, not in any absolute sense. There is only motion you can feel, motion you cannot feel, and the very convincing illusion that when nothing is obviously shaking you, nothing must be moving. This video is going to dismantle that illusion completely and permanently. We are going to start with the motion closest to you, the spin of the planet itself, and then we are going to zoom outward through every nested layer of movement stacked on top of it, through the orbit around the sun, through the solar system's long arc around the galaxy, through the galaxy's own careening path across the cosmic web, all the way out to the very edge of what instruments can measure, and the beginning of what physics has not yet resolved. By the time we are done, the stillness you feel in your chair will have been revealed for what it actually is. One of the most elaborate and complete perceptual illusions the universe has ever constructed around a conscious mind. Let us start with the spin. Right now, depending on where you are on this planet, your body is being carried eastward through space at somewhere between 0 and approximately 1,674 kilometers per hour. If you happen to be anywhere near the equatorial belt, in equatorial Africa, in Indonesia, in Colombia, in Kenya, in the Pacific Islands of Polynesia, then you are moving faster than the speed of sound in open air. The speed of sound in air at sea level is roughly 1,235 kilometers per hour. You are outpacing it continuously, without so much as feeling a breath of wind on your face because of it. That number, 1,674 kilometers per hour, comes directly from the geometry of the planet and the duration of its rotation. Earth's equatorial circumference is approximately 40,075 kilometers. The planet completes one full rotation every 23 hours, 56 minutes, and 4 seconds. This slightly odd number, shorter than the 2 4-hour day we are all familiar with, is called the sidereal day. It is the time it takes Earth to rotate exactly 360 degrees relative to the distant stars. The 2 4-hour solar day is slightly longer because during those 23 hours and 56 minutes, Earth has also traveled a small distance further along its orbit around the Sun, so the planet has to rotate just a little bit more before the Sun reappears in the same position in the sky. Divide the equatorial circumference of 40,075 kilometers by 23.93 hours, and you get the equatorial rotation speed of 1,674 kilometers per hour. But that maximum speed applies only at the equator. The further you travel from the equator toward either pole, the narrower the circle your line of latitude traces out in a single day, and therefore, the slower you move. The formula is straightforward. Multiply the equatorial speed by the cosine of your latitude. At 45 degrees latitude, which runs through northern France, Croatia, the northern United States, southern Canada, and northern New Zealand, the rotational speed drops to about 1,184 kilometers per hour, still comfortably supersonic. At 60 degrees latitude, which covers most of Scandinavia, much of Alaska and Russia, and the southern tip of South America, the speed is around 837 kilometers per hour. At 75 degrees, you are down to about 433 kilometers per hour. Stand precisely on the geographic North Pole or South Pole, and you are simply rotating on the spot. One full turn per day, no translational speed at all, just a silent pirouette as the rest of the planet turns around you. Now, here is the question that makes this genuinely interesting, rather than just a calculation exercise. If you are being carried eastward at 1,674 kilometers per hour, why do you feel absolutely nothing? Why does the room around you seem perfectly still? Why does every drink, every candle, every hanging light fixture in your environment behave as if it is at rest? The answer is one of the most beautiful and counterintuitive ideas in all of classical physics, and it is called the principle of inertial reference frames. When an object moves at a constant velocity, and here constant means both constant speed and constant direction, it is said to be in an inertial frame of reference. Inside an inertial frame, every physical process behaves identically to how it would behave if the object were completely stationary. There is no experiment you can perform inside the cabin of a smoothly cruising airplane that will tell you whether the plane is moving at 900 kilometers per hour or sitting parked on the tarmac. You can pour a drink, bounce a ball, light a candle, do a handstand. The physics is identical in both cases. The only time you feel anything is when the velocity changes, when the plane accelerates down the runway, or hits turbulence or banks into a turn. Change is what the body detects. Constant motion is invisible to biology. Earth's rotation is technically not a perfectly constant linear velocity, because rotation involves a constant change in direction and is therefore a form of continuous acceleration. But the centripetal acceleration at the equator due to Earth's rotation is astonishingly gentle. It works out to approximately 0.034 meters per second squared. Gravity, for comparison, pulls you toward the center of the Earth at 9.8 meters per second squared. The centripetal acceleration of rotation is less than 0.35% of that. Your vestibular system, the balance and acceleration detection system in your inner ear, has nowhere near the sensitivity to register such a tiny and continuous acceleration. The ground feels solid and still because, relative to everything around you, which is all moving at the same rotational speed, it functionally is. The same principle that makes rotation imperceptible to you also applies to the atmosphere above you and the oceans around you. Both are co-rotating with the planet, dragged along by gravitational attraction and molecular friction into the same synchronized spin as the surface beneath them. The enormous mass of air above the Sahara is not being left behind as Earth rotates. It is moving with the surface at essentially the same speed. The Pacific Ocean is not staying still while Asia spins away beneath it. Everything is turning together in one coherent, layered system. The one place where this perfect co-rotation breaks down, the one place where you can actually detect the underlying spin of the planet in the behavior of the world around you, is in the dynamics of large weather systems. When a low-pressure system forms and air starts flowing inward toward the center, the air masses coming from different directions are already moving at slightly different velocities because they originated from different latitudes, where the rotational speed was slightly different. This mismatch, when combined with the fact that the ground beneath the air is rotating, causes the incoming air to be deflected. In the northern hemisphere, this deflection is to the right. In the southern hemisphere, it is to the left. The result is that hurricanes and cyclones spin counterclockwise in the northern hemisphere and clockwise in the south. Every satellite image of a tropical storm, every sweeping spiral of clouds and wind, is the rotation of the planet writing its signature in the sky in letters hundreds of kilometers tall. The Coriolis effect operates at other scales too. Long-range artillery must account for it. Artillery shells fired over distances of more than a few kilometers will land noticeably off target if the rotation of the Earth is not calculated into the firing solution. Sniper schools teach students the Coriolis correction for extreme long-range shots. The rotation of the Earth is real enough that accurate weapon systems cannot ignore it. The ground really is spinning, and anything moving freely above it for long enough will drift relative to the surface. There is also something quietly extraordinary about the fact that Earth's rotation is not eternal and fixed. It is slowing down, continuously, measurably, because of the tidal interaction between Earth and the Moon. The Moon's gravity creates two tidal bulges in Earth's oceans, one on the side facing the Moon and one on the far side. Because Earth rotates faster than the Moon orbits, these tidal bulges are dragged slightly ahead of the Moon's position. The Moon's gravity then pulls backward on these advanced bulges, creating a subtle braking torque on Earth's rotation. Over long timescales, this torque is gradually stealing angular momentum from Earth's spin and transferring it to the Moon's orbit. The current rate of slowing is approximately 1.4 milliseconds per century. One day is getting about 1.4 milliseconds longer every 100 years. This sounds trivially small, and over any human lifetime, it is completely undetectable without atomic clocks. But over geological time, it adds up dramatically. About 4 billion years ago, a day on Earth lasted only around 6 hours. The planet was spinning roughly 4 times faster than it does today. The tides in the ancient ocean were enormous. The sky rotated at dizzying speed, and the young moon hung much closer and appeared much larger in the sky, because the same angular momentum transfer that is slowing Earth's rotation is simultaneously pushing the moon slowly away from us. We know the current rate of lunar recession with remarkable precision, about 3.8 centimeters per year, a measurement achieved by bouncing laser pulses off retroreflectors left on the lunar surface by the Apollo missions and timing the round trip. It is one of the most precise distance measurements ever made. The moon is moving away from us at the rate your fingernails grow. Earth's rotation is slowing at the rate of milliseconds per century. Both of these motions are real, ongoing, and leaving their marks in the geological record. Ancient tidal rhythms preserved in layered sedimentary rocks, called tidalites, show the periodicity of tides hundreds of millions of years ago and confirm that days were shorter and the moon was closer in deep geological time. Before moving to the next scale of motion, there is one more complexity worth mentioning: the wobble of the axis itself. Earth does not rotate around a fixed, immovable axis. The axis itself moves in space. The most dramatic of these axial motions is called precession, sometimes called the precession of the equinoxes. It works exactly like a spinning top that is tilted slightly off vertical. When you spin a top with its axis at an angle, the top's axis slowly sweeps out a conical path rather than staying in one orientation. Earth does exactly this, for the same physical reason. The sun and moon exert gravitational forces on Earth's equatorial bulge, that slight widening of the planet at the middle caused by its spin, and these forces create a torque that causes the rotation axis to slowly sweep through space. The precession cycle takes approximately 25,772 years to complete. Right now, Earth's North Pole points almost toward Polaris, the North Star, which is why Polaris holds its special position in navigation and culture. But this is a temporary arrangement. About 5,000 years ago, the pole pointed more toward a star called Thuban in the constellation Draco. Thuban was the North Star when the ancient Egyptians were constructing the pyramids. About 12,000 years from now, the axis will have swung around toward Vega, one of the brightest stars in the sky, and future civilizations, if any exist, will navigate by a completely different pole star. In about 26,000 years, the cycle will have completed and Polaris will be the North Star again. This precession has profound effects on Earth's climate over thousands of years. It changes the relationship between the tilt of the axis and the orbit around the sun, altering which hemisphere receives more intense sunlight in which season. Right now, Earth's northern hemisphere winter coincides with the period when Earth is closest to the sun, perihelion, in early January. But due to precession, this alignment changes over the 26,000-year cycle. In about 13,000 years, northern hemisphere winter will coincide with aphelion, Earth's farthest point from the sun, making northern hemisphere winters both darker and farther from the sun simultaneously. Southern hemisphere seasons will be the inverse. There is also a shorter, subtler wobble called the Chandler wobble, discovered in 1891 by the American astronomer Seth Carlo Chandler. The Chandler wobble has a period of approximately 433 days, and it causes Earth's rotation axis to trace a tiny, irregular circle about 9 meters wide when mapped onto the surface of the planet at the poles. The physical axis of rotation does not point to a single fixed geographic point. It traces a slow spiral, meaning the North Pole wanders slightly over time. The causes of the Chandler wobble are distributed across several geophysical systems: the redistribution of mass as ocean currents shift, changes in atmospheric pressure, the slow movement of the molten outer core, and even the mass redistribution caused by large earthquakes can slightly shift the position of the rotation axis. Every major earthquake subtly moves the pole. The 2011 Tohoku earthquake in Japan, one of the most powerful ever recorded, shifted Earth's rotation axis by about 17 centimeters. The Chandler wobble is the planet's rotation axis, responding to its own internal dynamics. All of this, every layer of the spinning motion, is happening right now. The floor you are on is spinning. The axis around which it spins is slowly precessing through the sky. That axis is wobbling on a 4-3-3 day cycle. The rotation itself is slowing. None of it is perceptible without instruments. All of it is real. If you are watching from somewhere right now, whether it is early morning, the middle of a quiet afternoon, late at night, take a moment to drop a comment below and let us know where in the world you are and what the time is there. It is honestly one of the most enjoyable parts of making these videos, seeing where they end up. And if you have not subscribed yet and you are enjoying this, hit subscribe. It helps more than you might think. Part 2. The long road around the sun. Now let us zoom out and consider the next layer of motion. The one that gives us years rather than days. The one that takes Earth on a journey 940 million kilometers long around the sun and brings it back to roughly the same relative position about 365 days later. This orbit has been going on for approximately 4.5 billion years. The planet has circled the sun roughly 4.5 billion times. And in all that time, the orbit has been stable enough to allow liquid water to persist on the surface for almost the entire duration, which is not a coincidence but one of the most remarkable facts about our position in the solar system. The orbit is not a circle. It would be more elegant, more satisfying to the geometric intuition, if it were. But planetary orbits are ellipses, a geometrical shape described by Johannes Kepler in the early 17th century, based on decades of painstaking observations by the Danish astronomer Tycho Brahe. Kepler published his first 2 laws of planetary motion in 1609, and they revolutionized astronomy not just by describing the shapes and speeds of orbits, but by implying, decades before Newton, that planets are not being guided by angels or crystalline spheres, but by a mathematical relationship between distance and gravitational force. An ellipse is a closed curve with 2 focal points rather than a single center. In Earth's orbit, the sun is not positioned at the geometric center of the ellipse, but at one of those 2 focal points. This means that for part of the year, Earth is closer to the sun than average, and for part of the year, it is farther away. The average distance between Earth and the sun, defined as 1 astronomical unit, is approximately 149.6 million kilometers. This is the anchor measurement of the entire solar system, the baseline against which all other planetary distances are expressed. But it is an average, and the actual range on either side is significant. At Earth's closest approach to the sun, a point called perihelion, the distance shrinks to about 147.1 million kilometers. At the farthest point, called aphelion, it stretches to about 152.1 million kilometers. The difference between perihelion and aphelion is roughly 5 million kilometers, about 3% of the average distance. Perihelion occurs in early January, around January 3rd or 4th each year. Aphelion occurs around July 4th. This is counterintuitive for anyone who grew up in the northern hemisphere and associates summer with warmth and winter with cold, because it means Earth is actually closest to the sun in what is winter in the northern hemisphere, and farthest from the sun in what is summer there. Distance from the sun is not what drives the seasons. What drives the seasons is the tilt of the axis. Earth's rotation axis is tilted about 23.5 degrees from perpendicular to the orbital plane. This means that, as Earth orbits the sun, different parts of the planet are angled more directly toward or away from the sun at different times of year. In June, the northern hemisphere is tilted toward the sun. Sunlight strikes it at a steeper angle, the days are longer, and the ground absorbs more heat per unit area. In December, the situation reverses. The northern hemisphere is tilted away. Sunlight strikes at a shallower angle. The days are shorter, and less heat accumulates. The seasons are a consequence of this tilt geometry, not of distance. You can verify the tilt effect yourself with a flashlight in a dark room. Shine it straight down onto a flat surface, and you get a bright, concentrated circle of light. Tilt the flashlight at an angle, and the same amount of light spreads over a larger elliptical area, producing a dimmer patch. The sun's light does exactly this with Earth's surface. In summer, In whichever hemisphere is tilted toward the sunlight is hitting like the straight-down flashlight. In winter, it is like the angled one. The distance from the sun barely matters compared to this angular effect. The elliptical orbit does have one real and measurable consequence for the seasons, however. Because Earth moves faster when closer to the sun, Kepler's second law, the equal areas law, and slower when farther away, the northern hemisphere's winter is slightly shorter than its summer. Earth is zooming through the perihelion part of its orbit in January, covering more of the orbital path per day, and crawling through the aphelion part in July. As a result, the winter season in the northern hemisphere lasts about 89 days, while summer lasts about 93 days. Those 4 missing days from winter have been there your entire life. You almost certainly never noticed. The speeds involved in this orbital motion deserve direct attention because they are remarkable. At perihelion, Earth is moving at about 30.29 kilometers per second. At aphelion, it has slowed to about 29.29 kilometers per second. The average orbital speed is approximately 29.78 kilometers per second, or about 107,000 kilometers per hour. To put that in concrete terms, at this speed you could travel from London to New York in under 2 minutes. You could circumnavigate the entire Earth in about 22 minutes. You could travel from Earth to the Moon, a distance of about 384,000 kilometers, in about 3.5 hours. And this is the casual, routine speed of the planet you live on, sustained year after year, millennium after millennium, across 4.5 billion years of continuous travel. The difference between perihelion and aphelion speed is about 1 kilometer per second. This might sound small, but it is the reason northern hemisphere winters are shorter. The planet is genuinely moving faster through space when it is closer to the sun, covering more of its orbital arc per day, spending less calendar time in that portion of the orbit. Kepler described this as a purely geometric relationship. The line connecting a planet to the sun sweeps out equal areas of space in equal times. Newton later explained it as a consequence of conservation of angular momentum, the same physical principle that makes a spinning ice skater speed up when she pulls her arms in. As Earth gets closer to the sun, it is in some sense pulling inward in its orbit, and like the skater, it picks up speed to compensate. On much longer timescales, the shape of the orbit itself changes slowly. The eccentricity of Earth's elliptical orbit, the measure of how stretched versus circular it is, currently has a value of about 0.0167, meaning the orbit is very nearly circular. But this value oscillates over a cycle of roughly 100,000 years under the gravitational influence of Jupiter and Saturn, whose enormous masses subtly tug on Earth's orbit as the solar system evolves. During periods of higher eccentricity, the orbit is more elongated. Perihelion brings Earth noticeably closer to the sun, and the seasonal imbalance caused by the distance variation becomes larger. During periods of near-circular orbit, the distance effect almost vanishes. This 100,000-year eccentricity cycle is one of the 3 components of what scientists call Milankovitch cycles, named after the Serbian astronomer and mathematician Milutin Milanković, who calculated their effects in the first half of the 20th century, with extraordinary patience and precision. Working before the era of computers, Milanković spent years solving the differential equations needed to calculate how solar radiation at different latitudes changed over time as a result of 3 orbital parameters: the eccentricity of the orbit, 100,000-year cycle, the obliquity or axial tilt, 41,000-year cycle, and the precession of the axis, roughly 26,000 years. But interacting with the orbit's own slow precession to produce a combined period closer to 23,000 years, Milanković was largely ignored or dismissed during his lifetime. His calculations predicted that ice ages should arrive and depart in rhythms driven by these orbital cycles, but the geological evidence available to confirm this was sparse and ambiguous. It was only in the 1970s when the oxygen isotope chemistry of ancient foraminifera preserved in deep-sea sediment cores became readable as a temperature record stretching back hundreds of thousands of years that his predictions were confirmed. The ice ages did follow the orbital rhythms. The periods of maximum glaciation, when ice sheets kilometers thick covered much of North America and Europe, coincided with periods when the orbital geometry was unfavorable to summer melting in the northern hemisphere. The interglacials, the warm periods between glaciations, coincided with orbital configurations that concentrated more summer sunlight on high northern latitudes. The 2.6-kilometer ice sheet that buried what is now Chicago 20,000 years ago, that carved the Great Lakes as it advanced and retreated, that piled glacial moraines across the landscapes of New England and the British Isles, that drove sea levels 120 meters below their current position and left the continental shelves exposed as dry land. All of that was ultimately driven by changes in the shape of Earth's path around the Sun and the tilt of the axis it spins on. The orbital mechanics of a small planet around an average star sculpted the whole quaternary ice age history of a world. We are currently in an interglacial period, the Holocene, which began about 11,700 years ago as the last glacial maximum ended. Human civilization has existed entirely within this warm interval. Agricultural societies, cities, writing, mathematics, science, industry, all of it has happened in a geological heartbeat of stable, warm conditions, and those conditions were arranged by orbital mechanics. The slight configuration of Earth's orbit that happened to be favorable for deglaciation around 20,000 years ago was what allowed the ice to retreat, the land to rebound, the seas to rise, and eventually, the conditions that allowed complex, settled civilization to emerge. What the Milankovitch cycles also tell us is that the current warming trend on Earth is happening against the background of orbital mechanics that predict a very slow, natural cooling. The orbit and tilt are not pushing the planet to warm right now. They are, by their slow logic, nudging it very gently toward another eventual glaciation over thousands of years. The rapid warming observed over the last century and a half is happening in the opposite direction to what orbital mechanics alone would suggest, which is one of the reasons the scientific consensus is clear that the current warming is driven by human emissions of greenhouse gases rather than by anything happening in the shape of the orbit. The orbit is patient. It will complete its slow eccentricity cycle. It will modulate the axial tilt through its 41,000-year rhythm. The precession will continue its 26,000-year sweep. Long after any current concerns about climate have either been resolved or not, the Milankovitch cycles will still be running, still scheduling ice ages and interglacials across the geological future, still encoding the geometry of the solar system's orbit into the chemical layers of ocean, sediment, and ice cores, waiting to be read by whatever minds exist to read them. Part 3. Racing around the Milky Way. Zoom out much further now, farther than the orbit, farther than the solar system, far enough back that the entire Earth-Sun distance becomes a tiny ring around a bright speck, and you can see that the speck is not at rest either. The Sun, along with every planet, every moon, every asteroid, every comet gravitationally bound to it, is orbiting the center of the Milky Way galaxy. It has been doing this for 4.5 billion years. It will continue doing this long after Earth is uninhabitable. The speed of this galactic orbit is approximately 230 kilometers per second, also expressed as about 828,000 kilometers per hour. This is not a small velocity by any human standard. At 230 kilometers per second, you could cross the entire diameter of Earth in about 55 seconds. You could travel from Earth to the Moon in under 28 minutes. You could reach the Sun in 3 days. This is the continuous, constant speed of the solar system through the Milky Way, maintained not by any engine, but by the gravitational balance between the Sun's orbital velocity and the combined gravitational pull of hundreds of billions of solar masses distributed throughout the galaxy. The Sun sits at roughly 26,000 light-years from the galactic center, positioned in what is called the Orion Arm, one of the minor spiral features of the Milky Way. The galaxy itself is a flattened disk, though calling it flat does not quite capture how extraordinarily thin it is relative to its width. The disk is perhaps 100,000 light-years across, but only about 1,000 light-years thick in the region where the Sun is located, a ratio similar to a vinyl record. The Sun is embedded in this disk, orbiting the central bulge of older stars that sits at the heart of the galaxy, not far from a massive black hole called Sagittarius A, which contains about 4 million solar masses in a region smaller than our solar system. At our distance from the center, The full circumference of the Sun's galactic orbit is approximately 163,000 light-years. At 230 kilometers per second, completing that circuit takes about 225 to 250 million years. This duration is called a galactic year, or sometimes a cosmic year, and it is one of the most useful units for thinking about deep time at the scale of the solar system's history. The Earth is currently about 20 galactic years old. The solar system has made roughly 20 complete circuits of the galaxy since it formed from a collapsing molecular cloud in the outer disk 4.5 billion years ago. When the solar system last occupied the position in the galaxy that it occupies now, the Permian-Triassic extinction event had just ended. The largest mass extinction in Earth's history, the event that killed roughly 96% of all marine species and 70% of all terrestrial vertebrate species, had just finished playing out. The world was in the process of recovering, beginning the long Triassic period that would eventually see the rise of the dinosaurs. The dinosaurs themselves rose and fell within a single galactic year. Everything from the first theropods in the Triassic to the asteroid impact 66 million years ago to the present moment. All of complex animal evolution since that impact, the radiation of mammals, the emergence of primates, the evolution of humans, the entirety of recorded history, all of it has occurred in the last roughly 0.3 galactic years, less than a third of one circuit around the Milky Way. On the scale of the galaxy's rotation, human civilization is not even a blink. It is a fraction of a single revolution. The Milky Way itself has been making its own internal rotations since its formation roughly 13.6 billion years ago. The oldest stars in the galaxy, those in the ancient halo surrounding the disk, have been completing galactic orbits since shortly after the Big Bang. The Sun is a relative newcomer, born about one-third of the way into the galaxy's history. Now, the galactic orbit is not as simple as a planetary orbit around the Sun. And this distinction matters for understanding what the solar system is actually doing. Planetary orbits are dominated by the overwhelming gravitational influence of a single central mass, the Sun, which contains 99.86% of all the mass in the solar system. The Sun's gravity defines the orbital mechanics almost completely. The galaxy's mass is distributed very differently. It is spread across hundreds of billions of stars, vast clouds of gas and dust, and a very large quantity of something that does not emit or absorb light, but does exert gravity, called dark matter. This distributed mass creates a gravitational landscape very different from the solar system's, and the result is that galactic orbits do not look like neat ellipses. One key difference is the bobbing motion. The solar system does not orbit the galaxy in a flat circle, staying at a constant height within the galactic disk. It oscillates above and below the galactic plane as it orbits. Think of it like a roller coaster that also travels in a large horizontal circle. The mass of the galaxy is concentrated in the disk, so when the solar system drifts above the plane, the gravity of everything in the disk below it pulls it back down. When it overshoots and goes below, the gravity above pulls it back up. This creates a periodic oscillation perpendicular to the orbital plane. The period of this vertical oscillation is roughly 60 to 70 million years for a complete cycle, meaning the solar system crosses the galactic midplane approximately once every 30 to 35 million years. The amplitude of this oscillation, how far above or below the disk the Sun travels at its maximum deviation, is approximately 250 to 300 light-years in the vertical direction. This is actually a significant fraction of the total disk thickness in the Sun's neighborhood. Right now, the Sun is positioned slightly above the galactic midplane, perhaps 30 to 100 light-years above it, depending on the model used, and it crossed the midplane only a few million years ago. It is currently climbing away from the plane and will reach its maximum height above the disk in approximately 14 million years before the disk's gravity pulls it back down. The combined orbital and vertical motion, when drawn in three-dimensional space relative to the galactic center, produces a path that looks something like a corkscrew wrapped around a very large circle. The solar system traces a spiraling, oscillating path through the galaxy, never quite repeating the same path, never quite returning to the exact same position, always weaving slightly above and below the plane as it sweeps around the center. There is an additional complication worth mentioning. The orientation of the solar system's own orbital plane relative to the galaxy's plane. The plane of the solar system, the ecliptic, is tilted at a significant angle to the galactic disk. The two planes are inclined to each other by roughly 60 degrees. This means the solar system is not moving through the galaxy like a wheel rolling in the direction of motion. It is more like a coin flipped at a steep angle, the planetary orbits cutting across the direction of galactic travel rather than aligning with it. This orientation changes over the galactic orbit, very slowly, because the angular momentum of the solar system's own internal rotation is conserved relative to the distant stars rather than rotating with the galaxy. After a quarter of a galactic orbit, roughly 60 million years from now, the ecliptic will be nearly edge-on to the direction of galactic travel. After half a galactic orbit, it will be tilted the other way. The galactic neighborhood through which the solar system travels is also not uniform. The Milky Way has spiral arms, regions of enhanced stellar density where stars and gas are more concentrated. The arms are not solid rotating structures, but rather density waves, something like a slow-motion traffic jam through which individual stars pass as they orbit. The Sun periodically passes through these denser regions as it orbits, experiencing different conditions in the interstellar medium and different densities of nearby stars. Some researchers have proposed that these passages through spiral arm density waves may have affected Earth's history by altering the cosmic ray environment or the frequency of close stellar encounters. The galactic center itself is a place of extraordinary activity. The massive black hole at the center, Sagittarius A, is relatively quiet at the moment, but the central parsecs of the galaxy, the innermost few light years, contain a dense cluster of young stars, intense radiation fields, and a complex magnetic environment. The entire central bulge of the galaxy, a region spanning thousands of light years, is rotating faster than the outer disk and contains a concentration of older, redder stars very different from the Sun's neighborhood. From our distance, this bulge appears as a faint smudge of light in the direction of the constellation Sagittarius, visible on dark nights as a thickening in the Milky Way's band. One galactic year ago, none of the familiar landscape of the solar system existed. The Earth had not yet formed. The Sun was a molecular cloud beginning its collapse. Every 225 million years, the solar system returns to approximately the same region of the galaxy, though never to the exact same position, because the galaxy's structure itself evolves over those timescales. The spiral arms shift, stars are born and die. The neighborhood changes. We have made 20 of these journeys. We have no reason to think we will not make many more. Part 4. The Milky Way's own racing motion. Let us zoom out one more enormous step and ask what the galaxy itself is doing. Everything we have discussed so far, the spin of the planet, the orbit around the Sun, the solar system's galactic circuit, all of that motion happens inside the Milky Way. Now we need to look at where the Milky Way is going. The answer, in the most direct terms, is that the Milky Way is moving through the universe at several hundred kilometers per second in the direction of a region of sky that we spent decades unable to see directly. It is being pulled by something enormous and partially hidden, and it is simultaneously being pushed by something equally enormous from the opposite direction. The full picture of the Milky Way's motion through the large-scale structure of the universe is one of the more recent and more dramatic discoveries of modern cosmology, and it involves structures so large that the human mind has no natural intuition for them at all. Begin with what is closest. The Milky Way is approaching the Andromeda Galaxy. Andromeda, officially called Messier 31, is the nearest large spiral galaxy to the Milky Way, sitting at a distance of about 2.5 million light-years. Despite that immense distance, Andromeda is gravitationally bound to the Milky Way, meaning the two galaxies are close enough and massive enough that their mutual gravity overwhelms the expansion of the universe. At this scale, they are falling toward each other. Current measurements indicate they are approaching at roughly 110 kilometers per second in the radial direction, though there is also a transverse component to the motion, meaning they are not on a head-on collision course, but will likely have a glancing encounter. The collision is predicted to begin in approximately 4.5 billion years. When it does, it will not be a catastrophic smashing of solid objects. Galaxies are mostly empty space. Individual stars are so far apart that even in a galactic collision, the probability of two stars actually hitting each other is negligibly small. What will happen is a gravitational interaction on an enormous scale. The two disk galaxies will interpenetrate each other. Their stars' orbits will be scrambled by the combined gravitational field. Gas clouds will collide and trigger massive bursts of star formation. And over hundreds of millions of years, the two galaxies will merge into a single large elliptical galaxy, all the organized disk structure of both spirals, having been disrupted into a puffy, rounded mass of aging stars. This future merger is not a distant threat, but a scheduled event, as certain as the next perihelion. The fate of the Milky Way has already been determined by the masses and positions of the galaxies involved. Gravity is already drawing them together, has been drawing them together for billions of years, will continue drawing them together for billions more. The Milky Way and Andromeda, along with roughly 50 other smaller galaxies, including the large and small Magellanic Clouds, are members of the local group, a gravitationally bound cluster of galaxies spanning about 10 million light-years. All of these galaxies are held together by mutual gravity, and the whole local group is itself in motion through the larger universe. Astronomers in the 1970s noticed something puzzling about the peculiar velocities of galaxies in the local universe. Peculiar velocity is the technical term for the deviation of a galaxy's motion from the smooth expansion of the universe. If the universe were expanding perfectly uniformly with no lumpy structure, every galaxy would be receding from every other galaxy at a rate precisely proportional to the distance between them, following what is called the Hubble flow. But real galaxies deviate from this perfect flow because gravity from nearby concentrations of mass pulls them toward those concentrations, adding a velocity component that is not explained by simple expansion. This deviation is the peculiar velocity. When astronomers measured the peculiar velocities of galaxies in our neighborhood and in a large region of the sky toward the constellations Centaurus and Hydra, they found something surprising. The peculiar velocities were not random. They were systematically pointed in a consistent direction toward a region of sky in the constellation Centaurus. Something massive, something gravitationally powerful, was pulling everything in that part of the universe toward it. The pull was so consistent and so large-scale that it became known simply as the Great Attractor. The difficulty was that the Great Attractor lies in the direction of the zone of avoidance, the band of sky blocked from optical view by the dust and stars of the Milky Way's own disk. Looking toward the galactic plane in visible light is like trying to see through a dense fog bank. You simply cannot see the distant structure behind it. For years, the Great Attractor was identified by its gravitational influence on nearby galaxies, but could not be directly observed. Eventually, astronomers used X-ray and radio wavelengths that can penetrate the galactic dust, and they found what was responsible: the Norma cluster and the Centaurus supercluster, an enormous concentration of galaxy clusters containing tens of thousands of galaxies and an enormous quantity of hot gas and dark matter. The total mass of the Great Attractor region is estimated at roughly 10 quadrillion solar masses, 10 followed by 15 zeros. All of that mass is exerting a gravitational pull on the Milky Way, on the local group, on everything in the surrounding hundreds of millions of light-years. The local group is currently moving toward the Great Attractor at roughly 600 kilometers per second. This is the velocity of the entire local group measured, relative to the cosmic microwave background radiation, the all-sky glow of thermal radiation left over from when the universe was a hot, dense plasma about 380,000 years after the Big Bang. The CMB is as close to an absolute rest frame as cosmology possesses. Relative to it, the local group is moving at 630 kilometers per second, directed toward the region of sky containing the Great Attractor and the broader flow of structure in that direction. In 2017, a team of cosmologists identified another major player in driving the local group's motion: the dipole repeller. This is not an attractor, but its opposite. A repeller, in this context, is a region of space that is dramatically underdense, a great void in the cosmic web where there is much less matter than average. Because there is less mass in a void, the gravity pointing toward the void is weaker than the gravity pointing in the other directions, creating what amounts to a net push away from the void. The dipole repeller lies in almost exactly the opposite direction from the Great Attractor, and its lack of gravitational mass is pushing the local group away from it, while the great attractor pulls from the other side. Both forces contribute to driving the Milky Way's motion in the same overall direction. These enormous structures, the great attractor, the dipole repeller, the Shapley supercluster, and even larger concentration further in the same direction as the great attractor, are part of what cosmologists in 2014 identified and named as the Laniakea supercluster. The name comes from the Hawaiian words for immeasurable heaven, Laniakea, chosen to honor the tradition of Polynesian navigators who used celestial motion to find their way across the vast Pacific. Laniakea was formally defined by Brent Tully and his colleagues, not by the distribution of galaxies in space, but by the flow of galactic velocities. If you draw flow lines showing which direction every galaxy in a region is being gravitationally pulled, you find that all the flow lines within a certain enormous region converge on the same gravitational basin. Everything within Laniakea is falling toward the same center. Laniakea is defined as the entire region of convergent flow. The result is a structure approximately 520 million light-years across, containing about 100,000 large galaxies in 100,000 galaxy groups and clusters, with a total mass equivalent to roughly 100 million billion suns. Our local group sits near one edge of this supercluster, in what cosmologists describe as the outskirts, about 250 million light-years from the central basin, toward which everything in Laniakea flows. We are somewhere in the outer suburbs of one of the largest coherent gravitational structures in the observable universe, and we are slowly falling toward its center, a journey that will take billions of years to complete at our current pace, and may never fully complete because the expansion of the universe is competing with gravity at these scales. Even Laniakea is not the final layer. The Shapley supercluster, even more massive and even more distant, is pulling on the great attractor region, which means it is also pulling on us, adding to the direction of our cosmic motion. The Milky Way's trajectory through the universe is the vector sum of all these gravitational influences operating at progressively larger scales. Part 5. The corkscrew path, what Earth's trajectory through the universe actually looks like. Necking toward have identified all these different layers of motion. It is worth asking what Earth's actual path through the universe looks like when you try to draw it. The answer depends completely on what reference frame you use, and understanding why that is the case is crucial to understanding what motion actually means in a relativistic universe. In the simplest possible terms, if you plot Earth's position relative to the Sun, you get an ellipse, clean, closed, repeating every year. From this reference frame, Earth is tracing the same path over and over. If instead you plot Earth's position relative to the center of the Milky Way, the picture changes dramatically. Earth is not just doing its small annual ellipse anymore. The entire solar system is sweeping through an enormous arc around the galactic center at 230 kilometers per second. Earth's orbital motion around the Sun is a tiny perturbation on top of this much larger galactic motion. The resulting path is not a closed ellipse at all. It is a slowly looping, spiraling curve that wraps around the galaxy's center, never quite closing because the small elliptical orbit around the Sun adds a slight in and out variation to the larger galactic arc. Plot Earth's position relative to the CMB rest frame, accounting for all the motions simultaneously, and the picture becomes extraordinarily complex. The spinning of the planet, the orbit around the Sun, the galactic arc, the flow toward the great attractor, all of these combine as vectors, each pointing in a different direction, each operating on a different timescale. The result is a path through four-dimensional space-time that is unique at every moment. Earth has never been at any particular position in the CMB frame twice, and it never will be. The universe has expanded since Earth was last at any given position. The Milky Way has moved, and every other reference point has shifted. Every second, Earth occupies a unique location in the universe that it has never occupied before. This is not a metaphor. It is a literal geometric fact. Earth's path through the universe is a unique, non-repeating trajectory. The ground beneath your feet right now is in a position in the universe that it has never been in before and will never be in again. There is a piece of internet mythology worth addressing here, sometimes called the helical model, which became briefly viral several years ago when an animation showed the planets as trailing behind the sun in long helical arcs as the solar system moved through the galaxy. The animation was visually stunning, and the core idea behind it, that the planets trace paths through the galaxy that are more complex than simple ellipses when you account for the sun's galactic motion, is correct. But the animation also got some significant details wrong. It showed the ecliptic plane always perpendicular to the direction of the sun's galactic motion, depicting the planets as always trailing behind the sun in spirals that sweep in the direction of travel. The actual geometry is different. The ecliptic is currently tilted at about 60 degrees to the galactic plane, and the orientation changes over time as the solar system's internal angular momentum is conserved relative to distant stars rather than relative to the galaxy's rotation. The accurate picture, worked out carefully by astronomers at PBS Spacetime, among others, is something more interesting. Currently, with the ecliptic at about 60 degrees to the galactic plane, the planets do trace paths that look something like a squashed corkscrew through the galaxy. After a quarter of a galactic orbit, when the ecliptic will be nearly edge-on to the galactic plane, the planets will instead trace a path more like a great wheel, rolling in the direction of galactic travel, with Earth spending half its year ahead of the Sun and half behind it, as seen from the galactic direction. The shape of the path changes over millions of years as the orientation of the solar system's orbital plane shifts relative to the galaxy. The beauty of it is not diminished by the precision. It might actually be enhanced by it. Earth's path through the galaxy is not a simple corkscrew. It is a corkscrew that changes its shape over tens of millions of years, embedded in a larger oscillation above and below the galactic plane, which is itself inscribed in an enormous arc around the galactic center, which is itself being carried in the direction of the Great Attractor, at hundreds of kilometers per second. And here is perhaps the most vertigo-inducing fact about all of this. You are on that trajectory right now. Not in some abstract future, not in geological time, not in a conceptual frame. Right now, in this moment, as you watch this, Earth is moving through the Milky Way at 230 kilometers per second. The Milky Way is moving toward the Great Attractor at 600 kilometers per second. And you are along for every bit of the ride, completely insulated from feeling any of it by the deep and unbreakable law that constant velocity is indistinguishable from rest. Part 6. The galaxies bobbing and the deep biological connection. The solar system's vertical oscillation through the galactic disk, the bobbing motion we mentioned briefly in the galactic orbit section, is worth examining in much greater depth because of a remarkable and somewhat unsettling connection it has to Earth's biological history. Recall the basic physics. As the solar system orbits the Milky Way, it does not stay perfectly in the equatorial plane of the galaxy's disk. It oscillates above and below the plane, with a period of roughly 30 to 35 million years from one crossing to the next. When the solar system is above the plane, the mass of the galaxy below it gravitationally accelerates it downward. When it passes through and is below the plane, the mass above accelerates it back upward. The oscillation continues indefinitely, like a pendulum with a very long period. The current position of the solar system is slightly above the galactic midplane, perhaps 30 to 100 light-years above it depending on the model and how you define the midplane, having crossed it only about 2 to 3 million years ago. We are currently climbing upward, away from the dense midplane, and will continue doing so for roughly another 14 million years before reaching maximum height and beginning to fall back. The galactic environments at the midplane and above it are meaningfully different. The midplane is the region of highest stellar density, highest concentration of molecular gas clouds, highest density of dust. When the solar system passes through the midplane, it is deep in the thickest part of the galactic disk, surrounded by the highest density of other stars, most exposed to the collective gravitational influences of the densest part of the galaxy. Some research groups have proposed that these midplane crossings may have been disturbing the outer Oort cloud, the vast, spherical reservoir of comets surrounding the solar system at distances of 10,000 to 100,000 astronomical units. The Oort cloud contains perhaps several trillion comets, very loosely bound to the Sun's gravity, sensitive to small perturbations from passing stars or molecular clouds. If the solar system's passage through the dense galactic midplane brought it into closer proximity with more stars and more massive gas clouds, the gravitational tidal forces from these encounters could periodically perturb the Oort cloud, sending a shower of comets into the inner solar system and increasing the rate of impacts on Earth. This hypothesis, the idea that the galactic plane crossings may trigger periodic cometary bombardments, was proposed in the 1980s and has been revisited numerous times since. The evidence for it is mixed. Mass extinctions do not appear to follow a perfectly regular 3-0 million-year clock when you look at the detailed fossil record. There is significant noise in the data and significant uncertainty in the exact timing of galactic crossings. But the correlation has not been entirely ruled out either, and some research continues to find suggestive periodicities in biodiversity data on timescales consistent with the galactic oscillation. More recently, a 2025 study in paleoceanography and paleoclimatology analyzed the origination rates of marine microorganisms across the entire Phanerozoic eon, roughly 540 million years of complex animal life, and found a statistically significant correlation between periods of the solar system's galactic oscillation and fluctuations in microplankton diversity. The proposed mechanism was cosmic ray exposure. As the solar system rises above or dips below the galactic disk, the galactic magnetic field's shielding properties change, and the flux of extragalactic cosmic rays reaching Earth varies. Higher cosmic ray doses could affect DNA damage rates in organisms, alter cloud cover and climate, or influence atmospheric chemistry in ways that affect global ecosystems. What this research line suggests, however tentatively, is that the trajectory of the solar system through the galaxy is not entirely irrelevant to the history of life on Earth. The cosmos reaches inward. The specific path the solar system has traced through the galactic disk over the past 540 million years may have shaped, at least in part, the biological diversity of life on this planet. The mass extinctions that cleared the stage for new evolutionary radiations, the periods of enhanced speciation that followed them, the oscillations of global climate that drove adaptation and extinction across geological time, these may carry within them an imprint of our position in the galaxy's plane. This is a genuinely remarkable possibility. The organisms that evolved to become us were shaped not only by local geology, chemistry, and climate, but by the trajectory of the solar system through a spiral galaxy. The path of the planet through the cosmos is written, perhaps, in the molecular structure of every living thing on the surface of it. Part 7. The expanding universe and the motion that is not motion. Here we reach the point where the usual framework of motion, the idea of things moving through space from one place to another, starts to require a significant modification. Because the universe itself is expanding, and the expansion of the universe is not a motion through space, it is a growth of space itself. Edwin Hubble established the expansion observationally in 1929, though the theoretical prediction had already been made by Alexander Friedmann in 1922 and Georges Lemaître in 1927, based on Einstein's general relativity. Hubble measured the distances to dozens of galaxies using Cepheid variable stars as standard candles, and plotted those distances against the recession velocities determined from the redshift of the galaxy's light. He found a clear and simple linear relationship. The farther away a galaxy was, the faster it appeared to be receding from us. This Hubble law was the first observational proof that the universe is not static, but dynamic, not a permanent and eternal stage, but something that has been evolving since a beginning in time. The key conceptual shift required to understand what this expansion means is the distinction between motion through space and expansion of space. When a galaxy at 1 billion light-years appears to be receding from us at some hundreds of kilometers per second, it is not necessarily moving through space the way a car moves down a highway. The space between us and that galaxy is growing, and the galaxy is being carried along with it. Think of dots on the surface of a balloon being inflated. As the balloon expands, every dot moves away from every other dot, not because the dots are rolling across the surface, but because the surface itself is growing. The expansion of the universe is something like this, though the analogy is imperfect because the universe does not have an outer surface and is not expanding into anything larger. The rate of this expansion is described by a number called the Hubble constant, denoted h0. Its value is approximately 70 kilometers per second per megaparsec, though the precise value is currently the subject of significant scientific debate known as the Hubble tension. A megaparsec is about 3.26 million light-years. The Hubble constant says that for every megaparsec of distance between 2 points in the universe, those 2 points are moving apart due to expansion at about 70 kilometers per second. 2 points separated by 10 megaparsecs are moving apart at about 700 kilometers per second. At around 4,300 megaparsecs of distance, objects are receding from us at the speed of light, meaning the universe has an effective edge beyond which we cannot see or receive information, even in principle. This expansion does not affect gravitationally bound structures. Within the local group, gravity dominates, and the expansion is irrelevant. Within the Milky Way, within the solar system, within the Earth itself, the expansion of the universe has no effect whatsoever on the structures or scales we interact with. The expansion is only significant over distances so large that there is no gravitational binding to compete with it, distances of hundreds of millions of light-years and more. But in 1998, astronomers discovered something that changed the story. The expansion of the universe is accelerating. Two independent teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were studying a type of exploding star called a Type Ia supernova, which has a predictable intrinsic brightness that makes it usable as a standard candle for measuring cosmic distances. When they plotted their supernova distances against recession velocities, they found that the supernovae were farther away than expected for their recession speed, meaning the universe had been expanding more slowly in the past than it is today. The expansion rate had been increasing. Something was causing the universe to accelerate its expansion over time. This discovery won Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. The thing causing the acceleration has been named dark energy, and it remains one of the most profound mysteries in all of physics. Dark energy constitutes approximately 68% of the total energy content of the observable universe. Ordinary matter, everything made of protons, neutrons, and electrons, everything that makes up stars, planets, and living things, constitutes only about 5%. Dark matter, which does not emit or absorb light but does exert gravity, makes up about 27%. The universe is overwhelmingly composed of things we do not understand. The atoms that make up everything you have ever touched or seen are a small minority of the universe's content. The nature of dark energy is genuinely unknown. It might be the energy density of empty space itself, a property of the vacuum that Einstein called the cosmological constant when he first wrote it into his equations and then famously removed it, declaring it his greatest blunder when it seemed the universe was not static. When accelerating expansion was discovered, the cosmological constant came back, rehabilitated, or dark energy might be something that evolves over time, a dynamical field that changes its behavior as the universe ages. Or it might indicate that general relativity needs to be modified at cosmic scales. These possibilities are all being actively investigated. The accelerating expansion is one of the strongest empirical facts in modern cosmology, confirmed by multiple independent methods. Its cause is not. The long-term consequence of this acceleration is significant. As the expansion continues to speed up, galaxies that are currently within our observable universe will eventually recede beyond the cosmic horizon, the boundary beyond which recession exceeds the speed of light and no communication is possible. The Milky Way and Andromeda will merge in about 4.5 billion years, and the combined galaxy will remain gravitationally bound. The local group will remain bound, a small island of gravity in an otherwise expanding void. But galaxies beyond the local group will recede. In perhaps 100 billion to a trillion years, the universe visible from the merged Milky Way-Andromeda galaxy will be nothing but the local group's stars in an otherwise dark, empty sky, all other galaxies having long since passed beyond the horizon. The expansion of the universe is the largest motion there is. It is the motion that contains all other motions. Earth's journey through the cosmos, its spin, its orbit, its galactic arc, its flow toward the great attractor, all of it happens inside a universe that is itself expanding outward in all directions, carrying everything with it, carrying even the things that are falling toward each other. because the expansion operates on scales so large that local gravitational dynamics are a small perturbation on top of it. Part 8. The speed accounting, start to finish. It is worth pausing here to do the complete accounting of Earth's velocity through the universe, because assembling the numbers in one place makes the scale visceral rather than abstract. Let us work from the smallest scale outward. Earth's rotational speed at your current latitude. If you are at the equator, this is 1,674 kilometers per hour, or about 0.465 kilometers per second. At 45 degrees latitude, it is about 1,184 kilometers per hour, or 0.329 kilometers per second. In any case, this is the smallest of all the velocities we will discuss, and is dwarfed by everything that follows. Earth's orbital velocity around the Sun averages approximately 29.78 kilometers per second, peaking at 30.29 kilometers per second at perihelion and dropping to 29.29 kilometers per second at aphelion. This is directed forward along the orbit, and at any given moment, it is pointed roughly at a right angle to the direction toward the Sunday. This velocity is about 64 times larger than the equatorial rotational velocity. It is the reason that even from the Sun's reference frame, Earth is always speeding along in a direction that is almost perpendicular to the Earth-Sun line. The Sun's velocity around the center of the Milky Way is approximately 230 kilometers per second, directed roughly toward the constellation Cygnus in the galactic orbit. This velocity is about 7.7 times larger than Earth's orbital speed. The solar system is moving through the Milky Way nearly 8 times faster than Earth moves around the Sun, and yet the orbital motion of Earth around the Sun is real and significant enough to cause measurable effects on the arrival times of signals from deep space pulsars when corrected for Earth's position in its orbit. The Milky Way's motion relative to the CMB rest frame is approximately 630 kilometers per second, currently directed roughly toward the constellation Leo. This is the result of the combined gravitational pull of the Great Attractor and the push of the dipole repeller. It is about 2.7 times larger than the solar system's galactic orbital velocity, and it is the largest single contribution to Earth's total velocity through the universe for much of the year. Adding these as vectors, accounting for the fact that they are not all pointing in the same direction, gives a total CMB frame velocity for Earth that varies over the course of the year as Earth's orbital velocity around the Sun adds to or subtracts from the other components. At different points in Earth's orbit, the orbital velocity is either partially aligned with or partially opposed to the galaxy's CMB frame velocity. The resulting total CMB frame velocity for Earth oscillates between roughly 350 and 700 kilometers per second, depending on time of year and precise geometry. Let us take a round number of 500 kilometers per second as a working estimate of Earth's typical velocity through the universe relative to the CMB. At 500 kilometers per second, in 1 second, Earth travels 500 kilometers. In the time you take to draw a slow breath, perhaps 3 or 4 seconds, Earth has moved 1,500 to 2,000 kilometers through the universe. In 1 minute, roughly 30,000 kilometers. In 1 hour, about 1.8 million kilometers. In 1 day, roughly 43 million kilometers. In 1 year, about 15.8 billion kilometers. Since you were born, if you are a young adult in your 20s, Earth has traveled approximately 300 to 400 billion kilometers through the universe in the CMB frame. This is not relative to anything local. It is relative to the fabric of space itself, measured against the most fundamental reference available. You have existed during roughly 300 to 400 billion kilometers of Earth's cosmic journey, and you felt none of it. Part 9. Relativity and the hidden dimension of motion. To this point, we have discussed motion entirely in terms of classical velocity, the idea of positions changing over time in three-dimensional space. But Einstein's special theory of relativity, published in 1905, added an insight that makes the full picture both more precise and more philosophically unsettling. Time itself is a dimension of motion, and you are always moving through it at the same total space-time speed. The central insight of special relativity is that space and time are not independent. They are aspects of a unified, four-dimensional structure called space-time, and every object in the universe is always moving through space-time at the same fundamental speed. The speed of light? 299,792 kilometers per second. Always, without exception. This speed is divided between motion through space and motion through time, and the two must always add up to the same total. When you are sitting completely still, not moving through space at all relative to your surroundings, your entire space-time speed is directed through time. You age at the maximum possible rate. Time passes for you as fast as it can for anything. When you start moving through space, some of your space-time speed is redirected from the time direction into the space direction. You move through time slightly more slowly than you did when you were stationary. The faster you move through space, the more of your space-time speed is devoted to space motion, and the less remains for time, and the more slowly you age relative to a stationary observer. This effect, called time dilation, is not an illusion or an approximation. It is real. It has been measured directly with atomic clocks, and GPS satellites would give incorrect position readings if engineers did not account for it. Clocks on satellites in high orbits run slightly fast compared to Earth-based clocks due to weaker gravity, a general relativistic effect, and slightly slow due to their orbital velocity, a special relativistic effect. The net effect must be corrected for every day to keep GPS systems accurate. For the speeds Earth is moving through the universe, the time dilation is small but real. At 500 kilometers per second relative to the CMB, Earth is moving at about 0.167% of the speed of light. The resulting time dilation factor is approximately 1.00000014. This means Earth ages about 1.4 parts per million more slowly than a hypothetical observer at rest in the CMB frame. Over 1 year, that difference is about 44 seconds. Over Earth's 4.5 billion year history, it amounts to roughly 200 years of difference. Not enormous on geological timescales, but not zero either. The deeper point of special relativity for this discussion is that motion through space is always coupled to motion through time. Every velocity we have discussed in this video is not merely a spatial velocity, but a space-time velocity, a rate of progress through the four-dimensional structure of the universe. Earth's trajectory through the cosmos is a four-dimensional path through space-time, and every point on that path is characterized not just by its spatial location, but by its temporal position. When astronomers say that we are 26,000 light-years from the galactic center, they are also implicitly saying that the light now reaching us from the galactic center left it 26,000 years ago. The spatial distance is inseparable from a temporal one. The map of the universe is simultaneously a map of the past. Every direction you look is a direction into a different era of cosmic history. The further you look, the earlier the universe you are seeing. When you look at the Andromeda galaxy and see it as a faint smudge 2.5 million light-years away, you are seeing it as it was 2.5 million years ago, before the first human beings existed. The universe you see is not a snapshot of right now. It is a layered record of the past, with closer objects showing more recent history, and farther objects showing progressively earlier epochs, all the way back to the cosmic microwave background, which shows us the universe as it was 380,000 years after the Big Bang, the earliest light that could have freely escaped the dense, hot plasma of the early universe. Earth's motion through spacetime is the story we have been telling all along, but understood now in its full depth. The spinning, orbiting, galactic racing, cosmic flowing, all of it is a trajectory through four dimensions. The stillness you feel is the local piece of all four dimensions around you, moving in the same way, at the same rate, so that none of the motion registers as a change from your perspective. The journey continues regardless. Part 10. The unknowns at the edge of the map. For all the precision with which astronomers and cosmologists have mapped Earth's motion through the universe, there are genuine edges to the known. Places where the measurements become uncertain, where the theories become contested, and where the most interesting science of the coming decades will be done. It is worth being honest about these edges, because they are where the story is still being written. The first major uncertainty is the detailed structure of the gravitational landscape pulling the Milky Way. The Great Attractor is identified, but the full three-dimensional mass distribution of the region, its extent, its exact location, The relative contributions of visible galaxies versus dark matter to its total mass are all incompletely mapped. The zone of avoidance continues to hide a significant fraction of the sky behind the Milky Way's disk. Next-generation radio surveys, which can map galaxy positions and velocities through the zone of avoidance, are gradually filling in this blind spot, but the picture is still incomplete. The dipole repeller was only formally identified in 2017. The precise structure of the void it represents, and its relationship to other large-scale underdensities in the cosmic web, is still being worked out. A 2023 paper in Astronomy and Astrophysics, using the Cosmic Flows 4 dataset, found that the dipole repeller and the cold spot repeller, two previously distinct underdense regions, now appear to form a single gigantic void. The cosmic web is more complex and more interconnected than any individual study has yet captured, and each new dataset reveals structure that previous surveys missed. The Hubble tension is one of the most actively debated problems in all of cosmology. The disagreement between the expansion rate inferred from the early universe (CMB) observations, roughly 67 kilometers (s/MPC), and the expansion rate measured using local standard candles, roughly 73 kilometers (MPC), represents either a systematic measurement error in one or both methods, or genuine new physics that the standard cosmological model does not account for. The James Webb Space Telescope has provided the most precise local distance measurements yet, and the tension persists. If it reflects real new physics, the implications could include modifications to the theory of dark energy, the existence of exotic particles in the early universe, or adjustments to general relativity at cosmological scales. There is also the question of what lies beyond the observable universe. The observable universe is defined by the cosmic horizon, the sphere around us from which light has had time to travel to us since the Big Bang. Its radius is about 46 billion light-years, larger than 13.8 billion, because expansion has been carrying distant regions away while the light traveled. Beyond this horizon there is more universe, but we cannot see it or directly measure its properties. We can infer from inflation theory that the universe likely extends far beyond the observable sphere, possibly infinitely, but the structure of that unobservable region is unknown. The question of whether structures beyond the observable horizon have gravitational effects on the observable universe is, in principle, testable. A phenomenon called the kinematic Sunyaev-Zeldovich effect allows astronomers to measure the bulk velocity of galaxy clusters by looking at how their hot gas perturbs the CMB. Alexander Kashlinsky and colleagues used this technique in 2008 to argue for a coherent large-scale flow, which they called dark flow, pointing in a consistent direction across a wide region of sky. They interpreted this as evidence of gravitational influence from mass concentrations beyond the observable horizon. The claim was controversial and was not confirmed by subsequent Planck satellite analyses. The current scientific consensus is skeptical of dark flow as an actual signal rather than a measurement artifact. But the methodology of looking for the fingerprints of structure beyond our horizon in the statistics of observed velocities is sound in principle, and the question will continue to be investigated as measurements improve. The nature of dark energy remains completely unresolved. Is it the cosmological constant, a fixed energy density of empty space? Or is it a dynamical field that might change behavior over time? Current observations from multiple sources are consistent with the cosmological constant interpretation, but the precision of those observations is not yet sufficient to rule out slowly evolving dark energy models. The Euclid Space Telescope, launched in 2023, and the Rubin Observatory Legacy Survey of Space and Time are designed partly to constrain the behavior of dark energy more tightly by measuring the cosmic expansion history and large-scale structure to higher precision than previously possible. These unknowns are not signs of failure. They are the natural frontier of a science that has made extraordinary progress in understanding the universe's structure and dynamics. The known is genuinely remarkable. We can measure the velocity of the Milky Way to within about 15 kilometers per second by analyzing temperature fluctuations in the CMB. We can determine that the universe began 13.8 billion years ago to a precision of about 100 million years. We can map the large-scale structure of the cosmic web across 1 billion light-years, and trace the flow of galaxies toward attractors and away from voids. These are not trivial achievements. They represent centuries of observation, theory, and instrumentation, converging on an increasingly detailed picture of the cosmos. The edges of the map are not endpoints. They are invitations. Part 11. The human dimension living inside this motion. It would be easy, having gone through all of this, to feel somehow unmoored. The ground beneath you is spinning. The planet is racing around the Sunday. The solar system is sweeping through the galaxy. The galaxy is streaming toward the great attractor. The universe is expanding beneath and around all of it. None of it feels like anything, and somehow that makes it both more remarkable and more vertiginous. The reason none of it is felt, to return to the principle from the opening section, is the fundamental equivalence of constant motion and rest. Your nervous system has no ability to distinguish between sitting in a room that is perfectly still and sitting in a room that is moving at constant velocity, whether that velocity is 30 kilometers per second or 230 kilometers per second or 630 kilometers per second. The velocity itself registers nothing. Only changes in velocity, only accelerations, produce a physical signal that the body can detect. Earth's orbital acceleration around the Sun is so small that it is thousands of times below the threshold of detection by the human vestibular system. The same is true for every other acceleration in this hierarchy of motions. They are all so gentle, so distributed over such large radii and such long timescales, that they are functionally invisible to biology. This perceptual limitation is not a flaw in the design of the human nervous system. It is a feature of the physics itself. The principle of equivalence, one of the foundations of general relativity, states that locally, a uniformly accelerating reference frame is indistinguishable from a gravitational field, and vice versa. What this means, at a deeper level, is that the concept of absolute rest is not physically meaningful. There is no experiment you can perform inside a closed laboratory that will tell you your absolute velocity, because there is no absolute velocity to measure against. The only velocities that are physically real are velocities relative to other things. This is why the question this video poses, how does Earth move through space, ultimately has no single answer. It has many correct answers, each one dependent on the reference frame. Relative to the Sun, Earth traces an ellipse at about 30 kilometers per second. Relative to the galactic center, Earth is racing at about 230 kilometers per second on a vast arc. Relative to the CMB, Earth is moving at several hundred kilometers, as in a direction that combines all these motions. All of these are equally valid descriptions of the same motion, viewed from different perspectives. There is something philosophically rich about the fact that the most comprehensive reference frame available, the CMB rest frame, is not a reference frame belonging to any physical object in the universe. The CMB is not a surface or a substance. It is a pattern of radiation distributed through space, left over from an early hot, dense phase of the universe's existence. The frame in which that radiation looks isotropic, equally bright in all directions, is not the frame of any star, any galaxy, or any observer. It is a frame defined by the universe's largest scale symmetry. Using it as a reference for absolute motion is the closest thing cosmology has to a fixed backdrop, but even this is not absolute in any deeper metaphysical sense. It is simply the frame in which the universe looks most smooth. The Copernican revolution, the shift from an Earth-centered to a Sun-centered model of the solar system, was the first step in a long process of decentering the human perspective from the physical description of the cosmos. The step from heliocentrism to the realization that the Sun is one star among hundreds of billions in one galaxy was the second. The step from that to understanding that the Milky Way is one galaxy among hundreds of billions, itself moving through a vast and structured cosmic web, is the third. Each step has removed a privileged position that human intuition wanted to assign to Earth, and each step has revealed a deeper, more honest, and more astonishing picture. The planet you live on is not at the center of the solar system. The solar system is not at the center of the galaxy. The galaxy is not at the center of the universe. The universe may not have a center at all, or it may have a sense in which every point is simultaneously the center of its own observable sphere. The cosmos does not organize itself around any particular location or observer. It is indifferent to our position in a way that ancient cosmologies never quite imagined. And yet, from the surface of this moving planet, humans have been able to figure all of this out. Without leaving the ground for most of human history, people tracked the motions of planets, deduced the shape and size of the solar system, measured the distance to the stars, discovered the structure of the galaxy, mapped the cosmic web, and determined the velocity of the Milky Way relative to the echo of the Big Bang. This is arguably the most remarkable thing that has ever happened on this particular rock hurtling through the universe. A species of biological organisms, confined by evolution to the surface of a small planet, looked up and systematically worked out the structure of the cosmos they inhabit, the motions of everything they could see and many things they could not, to a precision that still seems almost impossible given the scale of what was being described and the smallness of the tools doing the describing. Part 12. Final Synthesis. The journey that never repeats. Let us close by holding the complete picture in mind, all the layers at once. You are on a planet that spins on its axis once every 23 hours and 56 minutes. Depending on your latitude, that rotation carries you eastward at somewhere between 0 and 1,674 kilometers per hour. The axis is tilted 23.5 degrees, creating seasons. It is slowly precessing through a 26,000-year cycle, wobbling on a 433-day Chandler wobble, and the rotation is slowing by 1.4 milliseconds per century as the moon's tidal friction bleeds away angular momentum. That planet is orbiting the sun in an ellipse, moving at an average of 29.78 kilometers per second, covering 940 million kilometers in 365.25 days. The orbit's eccentricity changes on 100,000-year cycles. The axial tilt changes on 41,000-year cycles. The precession operates on 26,000-year cycles. Together, these Milankovitch parameters have driven the Ice Age rhythms of the last several million years and shaped the conditions in which human civilization emerged. The Sun, carrying you and the entire solar system, is orbiting the center of the Milky Way at approximately 230 kilometers per second. One complete galactic year takes roughly 225 to 250 million Earth years. Earth has completed about 20 of these. Layered on the circular galactic orbit is a vertical oscillation through the disk, crossing the midplane every 30 to 35 million years, potentially linked to variations in Earth's cosmic ray environment, and perhaps to patterns in the history of life. The solar system is currently slightly above the galactic midplane, having crossed it a few million years ago, and is slowly climbing further above it. The Milky Way itself is not at rest. It is part of the local group, approaching Andromeda at about 110 kilometers per second toward an eventual collision in 4.5 billion years. The local group as a whole is moving at approximately 630 kilometers per second relative to the CMB, driven by the gravitational pull of the Great Attractor and the Shapley supercluster in the general direction of Centaurus, and pushed by the dipole repeller in the opposite direction. Both the local group and the Great Attractor are part of the Laniakea supercluster, a 520 million light-year structure containing 100,000 galaxies, all flowing toward the same central gravitational basin. All of this is happening inside a universe that has been expanding since the Big Bang 8 billion years ago, and is currently accelerating in its expansion due to dark energy, whose nature remains one of the deepest unsolved problems in physics. Earth's total velocity relative to the CMB rest frame, accounting for all these contributions as vectors, is typically somewhere in the range of 350 to 700 kilometers per second, depending on the time of year and the phase of Earth's orbit. At 500 kilometers per second, a round number in this range, Earth is traveling through the universe at about 43 million kilometers per day. In the time it takes you to watch this video, roughly 2 hours, assuming you watch in real time, Earth will have moved about 3.6 million kilometers through the cosmos relative to the CMB. By every meaningful geometric measure, the position Earth occupies right now in the universe is a position it has never occupied before and will never occupy again. Every piece of that motion is silent, imperceptible, invisible without instruments, and completely real. The stillness of the room around you is not empty. It is the stillness of everything moving together, the air and walls and floor and your body, all carried in perfect synchrony by the same set of layered motions, the same rotation, the same orbit, the same galactic sweep, the same cosmic flow. When nothing around you accelerates relative to you, the physics of your nervous system has no way to distinguish that coordinated motion from rest. The physics of inertial frames is not playing a trick on you. It is being absolutely accurate. In your reference frame, you really are at rest. It is only when you compare your reference frame to a larger one that the motion becomes visible, and the frame in which all the motion is simultaneously visible is the largest one we know, the universe itself. The universe is not still. It has never been still. It began in motion, in the most violent expansion ever observed, and every structure that has formed since then has been in motion ever since, from the smallest particle to the largest supercluster. Motion is not something that happens to the universe. It is what the universe is made of, at every scale, from the quantum spin of particles to the galactic flow of matter across billions of light years. You are part of that motion. You have always been part of it. The journey continues with every breath, every heartbeat, every second that passes. The universe carries you forward, quietly and without ceremony, through positions in space and time that are unique, that have never been occupied and will never be occupied again, along a trajectory that will continue long after anything we currently know as Earth or humanity has ended. The still room and the silent night outside it are not a contradiction of this. They are its most perfect expression. The universe, in motion at every scale, arranged so precisely that the observer at the center of the motion feels only peace. If that gives you a different feeling about the ground you are sitting on right now, good. That is exactly what this kind of science is for. If you are new to this channel, subscribe, because we spend a lot of time here following these ideas wherever they lead, and they always lead somewhere worth going. If this video resonated with you, drop a like. It helps more people find their way here, and we will see you next time. Script for Spaceunk total, approximate word count, 27,000 plus words. Part 13, the solar wind, the heliosphere, and Earth's cosmic shield. There is a layer of Earth's cosmic journey that we have not yet discussed, one that connects the motion of the solar system through space to something tangible and protective, the heliosphere. Understanding the heliosphere turns the abstract concept of the solar system's galactic motion into something with direct physical consequences for the planet you live on. The sun is not merely a ball of burning gas sitting passively in space. It continuously ejects a stream of charged particles outward in all directions, electrons, protons, and helium nuclei, moving at speeds between 400 and 800 kilometers per second in what is called the solar wind. This continuous outpouring of charged particles inflates a vast bubble around the solar system called the heliosphere. The heliosphere is the region of space dominated by the sun's magnetic field and solar wind pressure, a protective cocoon that extends outward far beyond the planets into the surrounding interstellar medium. The boundary of the heliosphere, where the solar wind pressure drops to the point where the interstellar medium's pressure matches it, is called the heliopause. The Voyager 1 spacecraft, launched in 1977, crossed the heliopause in August 2012 and became the first human-made object to enter interstellar space. At the time of that crossing, Voyager 1 was approximately 18.1 billion kilometers from the Sun, or about 121 astronomical units. The heliosphere is enormous. It extends roughly 100 astronomical units in the direction facing the galactic wind and somewhat farther in the opposite direction, forming a roughly teardrop or comet-shaped structure, stretched by the motion of the solar system through the surrounding interstellar medium. The interstellar medium is the tenuous gas and dust that fills the space between stars. It is not empty. It contains hydrogen and helium at very low densities, trace amounts of heavier atoms, magnetic field lines, and a continuous flux of high-energy charged particles called cosmic rays. These cosmic rays come from violent events in the galaxy, supernova explosions, pulsar wind nebulae, and other energetic phenomena that accelerate charged particles to near the speed of light. Without the heliosphere, this cosmic ray flux would strike the solar system and Earth's surface much more directly. The heliosphere provides significant shielding against galactic cosmic rays. Inside the heliosphere, the solar magnetic field and the charged particle environment of the solar wind deflect and absorb many cosmic rays before they reach the inner solar system. Earth's own magnetic field, the magnetosphere, provides an additional layer of shielding within the heliosphere. Between the two, most cosmic rays are stopped or deflected before they penetrate to the surface in large quantities. The reason this matters for the story of Earth's motion through space is that the heliosphere is not a fixed, unchanging structure. It responds to changes in what the solar system is moving through. The density of the interstellar medium is not uniform across the galaxy. The solar system passes through regions of varying density as it moves along its galactic orbit. Currently, the solar system is passing through a relatively tenuous, hot region of the interstellar medium called the local bubble, a cavity in the interstellar medium thought to have been carved by supernova explosions over the past few million years. The local bubble is a region of unusually low-density interstellar gas, spanning roughly 300 light-years, and the solar system has been inside it for perhaps a few million years. When the solar system eventually exits the local bubble and enters a denser region of the interstellar medium, the heliosphere will be compressed. Higher external pressure from the interstellar medium will push the heliopause inward, shrinking the protective bubble. In a sufficiently dense interstellar cloud, the heliopause could be compressed to within the inner solar system, potentially reducing the shielding that currently keeps cosmic ray fluxes at the surface to their current levels. Models suggest that during periods when the solar system passes through dense molecular cloud material, which may happen every few 100 million years, cosmic ray fluxes at Earth's surface could increase substantially. Some researchers have proposed that such enhanced cosmic ray bombardment during these periods could have affected atmospheric chemistry, ozone layer stability, cloud cover, and even mutation rates in living organisms. The evidence for these effects in the geological and biological record is fragmentary, but the physical reasoning is sound. The heliosphere is also relevant to understanding how the solar system's tilt and orientation affect its interaction with the surrounding interstellar medium. As mentioned earlier, the solar system is currently moving through the interstellar medium at an angle, with the ecliptic plane significantly tilted relative to the direction of galactic motion. This affects the shape of the heliosphere. Data from the Voyager spacecraft and the Interstellar Boundary Explorer satellite suggest that the heliosphere has an asymmetric shape, bulging in certain directions, compressed in others, in a way that reflects both the direction of the solar system's motion through the interstellar medium and the influence of the interstellar magnetic field. The interstellar magnetic field itself, which permeates the interstellar medium outside the heliosphere, is tilted at a significant angle to the galactic plane. This tilt influences the shape and orientation of the heliosphere, essentially acting like an external magnetic environment that the solar system's own magnetic bubble has to push against. Understanding the detailed interaction between the heliosphere and the surrounding interstellar environment is an active area of research with implications for understanding the long-term cosmic ray history of the solar system and its potential biological effects. All of this connects back to the central theme. The motion of Earth through space is not merely an abstract astronomical fact. It has physical consequences for the conditions at Earth's surface. The solar system's trajectory through the Milky Way determines what kind of interstellar material it passes through, what kind of cosmic ray environment surrounds it, and how well protected the inner solar system is from the energetic particle radiation of the galaxy. The journey has consequences for the passengers. Part 14. The Moon's Influence on Earth's Trajectory. No discussion of Earth's motion through space would be complete without considering the role of the Moon, not just as an object orbiting Earth, but as a major modifier of how Earth moves and how it is oriented in space. The Moon is, in terms of relative size, the largest moon of any rocky planet in the solar system. While Jupiter and Saturn have moons that are larger in absolute terms, no other rocky planet has a moon as large relative to the planet itself as Earth's moon. The Moon contains about 1.2% of Earth's mass and exerts a gravitational influence on Earth that is constant, complex, and consequential across many timescales. The most direct gravitational effect is the tidal distortion of Earth's oceans and crust. The Moon's gravity creates a slight elongation of Earth's shape, pulling the side facing the Moon outward and, through inertial effects, also pulling the far side outward. As Earth rotates beneath these tidal bulges, the bulges sweep around the planet, creating the tidal rise and fall that coastal communities everywhere experience. This tidal friction, as discussed in the rotation section, is the mechanism by which the Moon is stealing angular momentum from Earth's spin and gradually slowing the rotation. But the Moon's influence on Earth's trajectory extends further. It stabilizes Earth's axial tilt. Without the Moon, computer simulations of the solar system suggest that Earth's axial tilt would undergo much larger variations over time, possibly wandering between near zero and 85 degrees over millions of years under the gravitational perturbations of the other planets, particularly Jupiter and Saturn. A tilt of 85 degrees would mean the poles receiving intense sunlight during their summer, while the equator received only oblique illumination, creating climate regimes wildly different from what Earth currently experiences. The Moon acts as a gravitational damper, stabilizing the axial tilt within a relatively narrow range of about 22 to 25 degrees over tens of thousands of years. This stabilization is important for maintaining climate conditions hospitable to complex life. A planet with a wildly oscillating axial tilt would experience extreme climate swings, far more dramatic than the Milankovitch cycles, potentially making it much harder for ecosystems to adapt and persist over geological time. This means that the Moon's presence may be one of the reasons Earth has been habitable for billions of years continuously. The gravitational damping effect of a large natural satellite may be a factor in planetary habitability that applies to rocky planets generally. A planet with a large moon may be more likely to maintain stable axial tilt, and therefore more stable climate conditions than one without. This is an active topic in the emerging field of planetary habitability science, with implications for the search for life on planets orbiting other stars. The Moon also affects the orbital mechanics of Earth-Moon system as a whole. The Earth-Moon barycenter, the common center of mass around which both bodies technically orbit, is located about 4,671 kilometers from Earth's center, which puts it inside the Earth but not at its center. Strictly speaking, it is the Earth-Moon barycenter that traces the precise ellipse around the Sun, while Earth wobbles slightly around this point as the Moon orbits. This wobble is small enough to be negligible for most purposes, but it is real and is used in precision astronomical calculations. Over geological time, the Moon's influence on Earth's rotation, tilt, and climate has shaped the conditions in which life evolved. The daily tidal rhythm that accompanies the Moon has influenced the behavior and physiology of every organism living in the coastal zone. The monthly tidal cycle drives spawning events in countless marine species. The stabilization of Earth's axial tilt has maintained climate regimes steady enough for complex ecosystems to develop and persist. The Moon is not a passive spectator of Earth's journey through space. It is an active participant, modifying the motion and the conditions in ways that have been consequential for the entire history of life. Part 15. Other Stars and Our Solar Neighborhood. The solar system is not moving through an empty galaxy. It is moving through a neighborhood populated by other stars, and those neighbors are themselves in motion, each on its own trajectory through the Milky Way. The stellar neighborhood around the Sun, the local volume within a few hundred light-years, contains thousands of star systems, and their motions relative to each other and relative to the Sun are measurable, meaningful, and occasionally significant. The nearest star system to the Sun is the Alpha Centauri system, a triple star system, approximately 4.37 light-years away. Alpha Centauri A and B are a gravitationally bound binary pair of stars, similar in size and temperature to the Sun, and they are accompanied by Proxima Centauri, a much smaller red dwarf that is currently the closest individual star to our Sun at 4.24 light-years. The Alpha Centauri system is moving relative to the Sun at about 22 kilometers per second, and current calculations suggest that Proxima Centauri will make its closest approach to the Sun in about 27,000 years, coming to within about 3 light-years before moving away again. The Sun moves through the local stellar neighborhood at about 20 kilometers per second relative to the average motion of nearby stars, a motion sometimes called the peculiar velocity of the Sun relative to the local standard of rest. This motion is in addition to the Sun's galactic orbit, which all nearby stars share approximately. The relative motions of nearby stars are like the individual motions of leaves floating on a river, each drifting slightly relative to the others, while all are carried in the same general direction by the current of the galactic rotation. Occasionally, the Sun passes close enough to another star system for the encounter to have potential effects on the outer solar system. By close, in this context, we mean within a light year or so, which is still an enormous distance by human standards, but is close enough for the gravitational tidal forces of a passing star to perturb the loosely bound comets of the Oort cloud. Records assembled from the Hipparcos and Gaia Space Telescope databases have allowed astronomers to trace the past and future trajectories of tens of thousands of stars near the Sun, identifying which ones have made or will make relatively close passes. The closest confirmed past encounter was probably the red dwarf star Schultz's star, which passed within about 0.82 light-years of the Sun, approximately 70,000 years ago, close enough to potentially have disturbed the inner Oort cloud and sent some comets inward through the solar system. Comet showers, triggered by stellar encounters, may take hundreds of thousands to millions of years to fully manifest, as the perturbed comets slowly spiral inward on their new trajectories. Looking forward, Gliese 710, an orange dwarf star currently about 62 light-years away, is calculated to pass within about 0.06 light-years of the Sun in approximately 1.3 million years. This will be the closest stellar encounter in the next few million years and will likely send a substantial perturbation through the Oort cloud. The potential comet shower resulting from this encounter would arrive in the inner solar system over millions of years following the encounter, increasing the impact rate on Earth. The timescales involved are far beyond any human civilization planning horizon, but they are part of the ongoing story of the solar system's journey through a populated galaxy. The density of stellar encounters varies depending on where in the galaxy the solar system is. In the dense spiral arm regions, stars are more closely packed, and encounters are more frequent. In the interarm regions where the Sun currently moves, stellar density is lower and encounters are rarer. The solar system's path through the galaxy continuously modulates the frequency with which it encounters other stars and the gravitational perturbations those encounters deliver to the Oort cloud. The impact history of Earth is, in part, the history of the solar system's galactic journey written in craters. Part 16. The Scale of Perspective. From electrons to superclusters. To close the intellectual arc of this video, it is worth taking one final step back and considering the complete range of spatial scales across which Earth's motion has physical consequences, from the subatomic to the supercosmic. At the smallest scales, the spin of the Earth affects the behavior of pendulums, the flight paths of large projectiles, the formation of weather systems, and the direction of ocean currents. The Coriolis effect is the mechanism by which the rotation of the planet reaches down into the physics of fluid dynamics and leaves its signature in every storm system that develops on the surface. This is the rotation of a planet a few thousand kilometers across, affecting atmospheric systems that span thousands of kilometers, detectable in anything that moves far enough or fast enough to accumulate the deflection over time. At the scale of the orbit around the Sun, the seasonal rhythms of climate, the Milankovitch cycles, the history of ice ages and warm periods, all of this reflects Earth's journey around a single star at 150 million kilometers distance. The life histories of every organism that has ever existed on this planet have been shaped by the orbital parameters of a rocky world around a middle-aged star. The ice ages that shaped the landscapes of continents, the evolutionary pressures they created, the dispersal of species across land bridges exposed by lower sea levels, all of it is encoded orbital history. At the scale of the galactic orbit, the vertical oscillation through the galactic disk, the passage through spiral arm density waves, the changing environment of the interstellar medium, these factors have potentially shaped the cosmic ray history of the Earth over hundreds of millions of years. The fossil record of life's diversity through the Phanerozoic may carry a faint imprint of the solar system's position in the galactic disk. At the largest scales, the flow of the Milky Way toward the Great Attractor and the Shapley supercluster, the membership in the Laniakea supercluster, the embedding in the cosmic web of filaments and voids, These define the context of the solar system's motion in the universe. They determine the direction and speed of our travel through the CMB frame. They situate the Milky Way within the largest structures that gravity has assembled in the observable universe. The entire range, from the Coriolis deflection of a storm cell to the galactic flow toward the Great Attractor, is the domain of Earth's motion through space. It is one continuous physical story, told across 20 orders of magnitude in spatial scale, from the hundreds of kilometers over which Coriolis becomes perceptible to the hundreds of millions of light-years over which the large-scale cosmic flow operates. The same fundamental physics connects all of these scales. Gravity, the curvature of spacetime by mass, operates identically whether it is curving the trajectory of a spinning mass of water vapor in the lower troposphere, bending the orbit of a planet around its star, sweeping a star system around a galactic center, or pulling a supercluster toward a denser neighbor. The equations are the same. The scale parameters are different, the geometry is different, but the underlying mathematics, Newton's laws as generalized by Einstein into general relativity, describes all of it with the same formal structure. The fact that the same laws govern motion from the scale of weather systems to the scale of the cosmic web is one of the deepest and most underappreciated aspects of physics. The universe is not divided into separate physical regimes governed by different rules at different scales. It is governed throughout by the same underlying laws, playing out on very different stages, producing very different phenomena, but ultimately connected by a single, consistent mathematical framework that human beings have spent the last 4 centuries assembling. Earth's motion through space is a manifestation of those laws at every scale simultaneously. The spinning, orbiting, galactic racing, cosmic flowing planet you live on is an advertisement for the universality of physics. Every layer of motion is a demonstration of the same gravitational geometry, played at a different tempo and on a different stage, connected through conservation laws and mathematical symmetries into one coherent and beautiful physical story. That story has been going on for 4.5 billion years. It will continue for billions more. You are living in a small chapter of it, on a small rock, in a corner of a galaxy, in a supercluster called Laniakea, in a universe 13.8 billion years old and still expanding. The motion never stops. The journey has no destination. And the stillness you feel right now is the universe, temporarily, perfectly, imperceptibly carrying you along. If any piece of this journey gave you a new way of thinking about the ground beneath your feet or the sky above your head, that is everything this kind of video is made for. Drop a comment, tell us what part hit differently for you, and let us know where in the world you are watching from. We genuinely read them. If you are new here, subscribe and come back. There is always more universe to explore. And if you found this valuable, sharing it is the best thing you can do to help more people find their way to it. See you next time. Part 17. The invisible architecture, dark matter, and the scaffolding of motion. Everything we have discussed about Earth's cosmic motion, from galactic orbits to large-scale flows, depends on knowing where the mass is. Mass is what creates gravity. Gravity is what governs motion. And one of the most unsettling facts in modern astrophysics is that most of the mass in the universe is invisible. Dark matter is not a new idea. Fritz Zwicky, a Swiss-American astronomer working at Caltech in the 1930s, first proposed that galaxy clusters contained far more mass than could be accounted for by the visible stars and gas. He found that the galaxies in the Coma cluster were moving so fast relative to each other that the cluster should have flown apart long ago if visible matter were all that held it together. Something else, something massive and invisible, had to be providing the gravitational glue. He called it Dunkel Materie, dark matter. Zwicky was largely ignored for decades. The confirmation came in the 1970s from American astronomer Vera Rubin, who was measuring how fast stars in nearby spiral galaxies rotated around their galactic centers. The expected pattern, based on Newtonian gravity applied to visible mass, was clear. Stars farther from the center should orbit more slowly, just as the outer planets of the solar system orbit the sun more slowly than the inner ones. Gravity weakens with distance from the concentrated central mass, so orbital speeds should drop off. What Rubin found was that they did not drop off. Stars at the outer edges of galaxies were moving just as fast as stars, much closer to the center. In some galaxies, outer stars were even moving slightly faster. The rotation curves were flat when they should have been declining. The only explanation was that the galaxies were embedded in vast, invisible halos of matter extending far beyond the visible disk, providing additional gravitational mass that kept the outer stars moving at their observed high speeds. The dark matter halo of the Milky Way extends to roughly 10 times the radius of the visible disk, perhaps 300,000 light-years or more from the galactic center. The total mass of the dark matter halo is roughly 5 to 10 times the mass of all the visible stars and gas in the galaxy. The solar system orbits not just within the visible disk, but within this enormous dark matter cocoon. The gravitational landscape that governs the Sun's galactic orbit is shaped as much by the dark matter halo as by the visible matter in the disk. This has direct implications for the accuracy of any description of Earth's galactic motion. When we say the Sun orbits the galactic center at 230 kilometers per second at a distance of 26,000 light-years, that orbital speed is the result of the combined gravitational field of all the mass inside the Sun's orbit, the visible stars, gas, and dust of the inner galaxy, the central black hole, and the dark matter within the Sun's orbital radius. Without dark matter, the Sun would be orbiting at a much lower speed, consistent with the mass of visible matter alone, and the outer disk of the Milky Way would be gradually losing stars into the intergalactic medium rather than maintaining the flat rotation profile that observations confirm. The nature of dark matter is one of the great open questions of physics. It does not emit, absorb, or reflect light. It does not interact via the electromagnetic force at all. It interacts gravitationally, and possibly through the weak nuclear force. The leading candidate for many years was a class of hypothetical particles called weakly interacting massive particles, or WIMPs. Enormous underground detectors filled with ultra-pure liquid xenon or germanium crystals have been searching for WIMPs for decades, looking for the rare collision between a dark matter particle and an atomic nucleus that would produce a faint recoil signal. So far, no confirmed detection has occurred. The search continues, with each new generation of experiments setting tighter and tighter constraints on what WIMPs could be and haven't found. Other dark matter candidates include axions, extremely light particles originally proposed to solve a different problem in particle physics, sterile neutrinos, primordial black holes formed in the early universe, and various other exotic possibilities. Each has its own experimental signatures and its own challenges. The evidence that dark matter exists as a physical substance is overwhelming. The galactic rotation curves, the gravitational lensing of background galaxies by galaxy clusters, the structure of the cosmic web as mapped by large surveys, the acoustic oscillations in the CMB, all point to dark matter as a real component of the universe. What it is made of remains unresolved. Dark matter does not just passively provide a gravitational scaffold for galaxies. It actively shapes the cosmic web. The initial fluctuations in the density of dark matter in the early universe seeded the formation of all large-scale structure. Because dark matter did not interact electromagnetically, it could begin clustering gravitationally earlier than ordinary matter, which was trapped in a photon-baryon fluid until recombination. Dark matter clumped first, forming gravitational wells. Ordinary matter then fell into these wells, forming galaxies inside dark matter halos. Every galaxy we can see is embedded in a dark matter halo, and the halos themselves are arranged in the filamentary cosmic web that mirrors the distribution of dark matter in the universe. The Laniakea supercluster, the cosmic web it belongs to, the great attractor, the dipole repeller, all of the large-scale structure that governs the Milky Way's motion through the universe, is shaped primarily by the distribution of dark matter. The visible galaxies are, in cosmologists' telling phrase, the lights on the Christmas tree. The tree itself, the structural skeleton, is dark matter. When the Milky Way flows toward the great attractor, it is flowing toward a concentration of dark matter as much as toward a concentration of visible galaxies. Understanding Earth's motion through the universe therefore requires understanding the distribution of invisible matter across scales of hundreds of millions of light-years. Matter that interacts only through gravity and possibly through a force too weak for current detectors to measure. The cosmic journey of our planet takes place inside a universe whose architecture is dominated by something we have never directly detected and do not yet understand. Part 18. The solar system's path as a cosmic odometer. One of the stranger implications of Earth's multi-layered motion through space is the idea that the trajectory itself is a kind of cosmic record, an odometer that has been running for 4.5 billion years. Every position the solar system has occupied in the galaxy, every interstellar cloud it has passed through, every spiral arm it has traversed, every stellar encounter that has perturbed the Oort cloud, all of these events have left physical traces in the solar system itself, and potentially on the geological and biological record of Earth. The chemistry of the solar system was set partly by the galactic environment at the time and place of the Sun's formation. The molecular cloud from which the Sun formed about 4.6 billion years ago was itself a product of galactic chemistry, enriched by the nucleosynthesis of stars that had lived and died before the solar system existed. The specific mix of elements in the solar system, the relative abundances of heavy elements produced in previous generations of stars, reflects the galactic neighborhood at the time of formation. As the solar system has traveled through the galaxy over 4.5 billion years, it has been bathed in varying levels of cosmic radiation, has passed through regions of interstellar medium with varying densities and compositions, and has experienced the gravitational perturbations of stellar encounters and molecular cloud passages. Each of these experiences has, in principle, left a physical imprint. The isotopic composition of meteorites, particularly ancient meteorites that have preserved pristine records of conditions in the early solar system, carries information about the nucleosynthetic history of the material that formed the sundae. Some meteorites contain microscopic grains, called presolar grains, tiny mineral crystals that formed in the atmospheres or outflows of other stars before the solar system existed and were incorporated into the forming solar system from the original molecular cloud. These grains have isotopic compositions reflecting the nuclear processes in their parent stars, making them cosmic fossils from the era before the Sun formed. The distribution of craters on the Moon, which preserves a longer record of impact history than Earth's geologically active surface, may carry information about the impact rate history of the inner solar system. If the galactic environment modulates comet showers into the inner solar system through Oort cloud perturbations, as discussed earlier, then the cratering record on the Moon might show periods of enhanced impact rate corresponding to the solar system's passages through denser galactic environments or closer encounters with other stars. Disentangling this signal from the noise of random impact statistics is difficult, but the principle is sound. The ice core records from Antarctica and Greenland, which extend back hundreds of thousands of years, preserve records of atmospheric composition, temperature, dust deposition, and cosmic ray intensity. Analysis of certain isotopes, particularly beryllium 10 and chlorine 36, which are produced by cosmic ray interactions in the atmosphere, can in principle track variations in cosmic ray flux over the time period covered by the ice cores. These variations reflect both solar activity, which modulates the heliosphere's cosmic ray shielding, and potentially longer-term changes in the galactic cosmic ray environment as the solar system moves. The chemical composition of the Earth's crust contains rare elements deposited by meteorites and micrometeorites, traces of the cosmic rain of material that has been falling onto Earth throughout its history. This cosmic input has been modest in absolute terms, but it includes elements like iridium, osmium, and platinum group metals that are rare in Earth's crust, but relatively abundant in meteoritic material. The famous iridium layer found worldwide in the geological record at the boundary between the Cretaceous and Paleogene periods, the KPG boundary 66 million years ago, provided key evidence that the mass extinction at that time was caused by a large impactor. Every layer of sediment on Earth contains a background drizzle of meteoritic material, a record of the solar system's continuous accumulation of cosmic debris as it moves through the galaxy. In this sense, the Earth is not just a passenger on a cosmic journey. It is also a recorder of that journey. The rocks, the ice, the atmosphere, the fossil record, all contain encrypted information about the solar system's path through the Milky Way. Reading that record fully would require understanding the trajectory precisely enough to correlate it with known features of the galactic environment, which is itself an incompletely mapped landscape. But the principle is real, and the tools to do this kind of galactic archaeology are improving with each new generation of telescopes, detectors, and computational models. Part 19. Relative motion, absolute motion, and the philosophy of where we are. It is worth taking a step back from the technical details one final time and asking a genuinely philosophical question. Does any of this have a meaning beyond the physical facts? Does knowing that you are racing through the universe at 500 kilometers per second change anything about the experience of being alive? The simple answer is that it does not change the physics of daily life in any direct way. The coffee in your mug cools according to thermodynamics that are entirely local. The chair supports you according to structural mechanics that are local. The screen displaying these words operates according to electromagnetism and quantum mechanics that function identically regardless of the frame of reference in which you observe them. The reference frame independence of physics is real and complete. The laws of nature do not depend on where you are in the cosmos or how fast you are moving through it. But there is a different kind of meaning that is not about daily physics. It is about context. It is about the relationship between the small, immediate world of experience and the vast, impersonal machinery of the cosmos within which that experience is occurring. The ancient picture of the cosmos placed Earth at the center of everything, not merely at the geometric center of the planetary orbits, but at the moral and theological center of reality. The heavens moved around Earth because Earth was what mattered. The motions of the celestial bodies were arranged for the benefit of the observers on the central planet, or at least were addressed to them. This picture was satisfying in the way that any story is satisfying when the narrative places you at the center of it. The scientific picture inverts this completely. Earth is not at any center. It is not even in a particularly notable position. It is a small, rocky world orbiting an average star in the outer disk of a barred spiral galaxy, roughly 26,000 light-years from the center, 2/3 of the way to the edge of the disk. The Milky Way is one of roughly 100,000 galaxy members of Laniakea. Laniakea is one of many superclusters in the observable universe, which contains perhaps 2 trillion galaxies in total. There is nothing about our position that marks it as special in any physical sense. And yet here is the other side of that coin, the one that is easy to miss when you are focused on how unspecial our position is. From this unremarkable position, using instruments built by organisms that evolved on this unremarkable planet, we have worked out the shape of the observable universe, the history of its expansion, the nature of its composition, the motions of galaxies at distances of hundreds of millions of light-years. We have identified the Great Attractor, the Dipole Repeller, the Laniakea supercluster. We have measured Earth's velocity relative to the CMB to within about 2 kilometers per second. We have traced the trajectory of the solar system through the galaxy well enough to propose connections between its vertical oscillations and the fossil record of life. This is not a small thing. It is, in fact, one of the most remarkable things that has ever happened anywhere that we know of. Matter organized itself into a self-aware configuration on the surface of a moving planet and figured out how it was moving. Not because it needed to for survival, not because there was any immediate practical benefit to knowing Earth's CMB frame velocity, but because the organisms on this planet are the kind that ask questions about the universe they live in and then build the instruments and develop the mathematics needed to answer those questions. The motion is real. The journey is ongoing. The universe is astonishingly large, astonishingly old, and indifferent to the existence of any particular planet or any particular species. None of that makes the journey less worth taking. It might make it more so. The ground beneath you is spinning. It is racing around the Sunday. The sun is sweeping through the Milky Way. The Milky Way is falling toward the Great Attractor. The Great Attractor is falling toward Shapley. The universe is expanding beneath all of it, carrying everything outward into a future whose ultimate shape depends on dark energy, whose nature we do not understand. And you, a temporary arrangement of atoms on a moving rock, are aware of all of this. You are made of matter that has been through stars. You are living on a planet that is 4.5 billion years into its galactic journey. You are capable of knowing this, and knowing that you know it, and finding it interesting. That is not nothing. In a universe this large and this old, that might be quite something. Part 20. Coda, the motions you carry home. By now, if you have stayed through all of this, you are carrying around a new kind of understanding of where you are. Not just geographically, not just nationally, not just on the surface of a planet, but cosmically. You are a point in a journey that has been going on for 4.5 billion years and will continue for billions more. The specific journey of Earth through the universe is one of the least repeating, most intricately layered paths in all of astrophysics. Tonight, if the sky is clear where you are, step outside and look up. If it is dark enough, you might see the Milky Way as a faint band of light across the sky. That band is the disk of the galaxy, seen from inside, the accumulated light of hundreds of billions of stars between you and the far side of the disk. The thickening toward the constellation Sagittarius, visible from the southern hemisphere or low in the southern sky from mid-northern latitudes in summer, is the direction of the galactic center, 26,000 light-years away. The direction you are moving as the solar system orbits the galaxy is roughly toward the constellation Cygnus, high in the summer sky. Look toward Centaurus, if you are in the southern hemisphere, or can see low in the southern sky from the tropics, and you are looking roughly in the direction of the Great Attractor, toward the concentration of mass that is pulling the Milky Way and all of Laniakea in its direction. Look toward Virgo, and you are looking roughly toward the center of the local supercluster's gravitational basin, toward the Virgo cluster, which sits at the heart of the region of space the local group has been streaming toward. Look in the direction of Leo, and you are looking roughly in the direction the Milky Way is moving relative to the CMB, the direction from which the CMB appears ever so slightly warmer, due to the Doppler blue shift of our motion. All of this is happening right now, silently and continuously. Whether you are looking at the sky or not, the journey does not pause for observers. The universe carries its passengers, whether they know they are passengers or not. But there is something about knowing. There is something about understanding the layered complexity of the motion, the spinning and orbiting and racing and flowing, that changes the quality of the stillness you feel when you stand in a quiet place and look up at the night sky. The stillness is not absence. It is the presence of motion so perfect, so completely shared by everything around you, that it feels exactly like rest. The universe is in motion. You are in motion with it. And the extraordinary thing, the thing that has made all of this worth 2 hours of your time, is that the motion is not random or directionless or empty. It is structured. It is governed by the same laws of gravity and momentum and conservation that operate everywhere, at every scale, in every corner of the observable cosmos. The spinning planet, the orbiting star, the racing galaxy, the flowing supercluster, all of it obeys the same mathematics, expressed at different scales, playing out on different time frames, telling the same fundamental physical story. That story began 13.8 billion years ago with the Big Bang, and it is still being told. Earth has been telling its chapter of it for 4.5 billion years. Whatever comes next in the story, we are still in the middle of it, still spinning, still orbiting, still racing through the Milky Way, still falling toward the Great Attractor, still alive, for now, in a universe that does not explain why it is the way it is, but that is, in every measurable detail, extraordinary. Go outside, look up, feel the stillness, know what it really is. Thank you for spending this time here. If you are watching for the first time, consider subscribing. This channel exists for exactly this kind of deep, slow, careful exploration of the cosmos, and there is always more to explore. Leave a comment below and let us know what part of this landed hardest for you, or what you want us to follow next. We read them, and we will be back. See you among the stars. Part 21. The language of motion, how we measure what we cannot feel. One thing this journey through Earth's cosmic motion raises, almost by necessity, is the question of how we know any of it. None of these velocities is directly perceptible. No human being has ever stepped outside the solar system to watch it move. No one has observed the Milky Way from outside. The measurements that underpin everything in this video were made from inside the system being measured, by instruments built on the surface of a moving planet, looking outward through layers of moving context. And yet the results are precise, reproducible, and internally consistent to an extraordinary degree. Understanding how that is possible is itself a remarkable part of the story. The most fundamental technique is the measurement of stellar parallax. As Earth orbits the Sun, nearby stars appear to shift their position slightly against the background of much more distant stars, because the angle from which we view them changes as Earth moves from one side of its orbit to the other. The nearest star to the Sun, Proxima Centauri, shows a parallax shift of about 0.77 arcseconds, a tiny angle that requires careful measurement but is well within the capabilities of modern instruments. From this parallax, the distance to Proxima Centauri can be calculated directly using basic trigonometry. For nearby stars within about 1,000 light-years, parallax is the most accurate direct distance measurement available. The European Space Agency's Gaia mission, launched in 2013 and still operating as of the mid-2020s, has measured parallax distances to more than 1 billion stars in the Milky Way with unprecedented precision. Gaia has also measured the proper motions of these stars, their actual movements across the sky, to an accuracy of a few millionths of an arcsecond per year. This data has allowed astronomers to trace the trajectories of millions of stars through the galaxy and reconstruct the three-dimensional velocity field of the solar neighborhood in extraordinary detail. From Gaia data, we can determine which stars are approaching the solar system and which are receding, which will have close encounters in the future, and how the local stellar population is moving relative to the galactic average. For the measurement of the Sun's galactic orbital velocity, the key technique involves measuring the proper motion of Sagittarius A, the supermassive black hole at the center of the Milky Way, as seen from Earth. If the Sun is orbiting the galactic center, then Sagittarius A times should appear to move across the sky relative to background galaxies and distant quasars, because it is the Sun's orbit that creates the apparent motion of the galactic center. Careful measurements of SCRA, A's proper motion using radio telescopes, have given the Sun's orbital velocity as approximately 220 to 250 kilometers per second, consistent with independent measurements from stellar kinematics. The measurement of the Milky Way's velocity relative to the CMB is done by analyzing the dipole anisotropy of the CMB itself. The CMB is, in the frame moving with the CMB radiation, almost perfectly isotropic, the same temperature in every direction. But because the Milky Way, the solar system, and Earth are all moving relative to this frame, the CMB appears slightly warmer in the direction of motion, because we are running toward those photons, and they are Doppler blue-shifted and slightly cooler in the opposite direction. The amplitude of this temperature asymmetry, measured precisely by satellites including COBE, WMAP, and Planck, gives directly the speed of the solar system relative to the CMB, approximately 370 kilometers per second in the direction of the constellation Leo. Correcting for Earth's orbital velocity around the Sun gives the Sun's velocity, and correcting further for the Sun's motion relative to the local group gives the local group's velocity of approximately 630 kilometers per second. The measurement of the large scale flows toward the great attractor and other structures is done using galaxy peculiar velocities. This requires knowing the distance to a galaxy independently of its recession velocity, which tells you the distance implied by simple Hubble expansion. If a galaxy is closer than its recession velocity suggests, it is moving toward us faster than the expansion alone would account for. If farther, it is moving away faster. The excess velocity is the peculiar velocity, driven by gravity from nearby structures. By mapping the peculiar velocities of thousands of galaxies using distance indicators like the Tully-Fisher relation and the fundamental plane, cosmologists reconstruct the three-dimensional velocity field of the nearby universe and trace it back to the mass concentrations driving it. Each of these techniques is an example of using the motion itself as a measurement tool. The parallax of stars uses Earth's orbital motion to create a baseline. The CMB dipole uses the solar system's motion to create a temperature asymmetry. The peculiar velocities of galaxies use their deviations from uniform Hubble flow to trace gravity. Motion that cannot be felt is revealed by the measurements it leaves in the physics of light and geometry. The history of these measurements is also the history of human beings gradually coming to understand the full scope of the cosmic journey they are on. In 1543, Copernicus proposed that Earth moves around the Sun, a claim that required courage to publish and decades to be accepted. By the early 20th century, the debate about whether the Milky Way was the entire universe, or merely one of many such structures, had been resolved by Edwin Hubble's measurement of the distance to the Andromeda Galaxy. By the 1970s, Vera Rubin's flat rotation curves had revealed that galaxies were immersed in dark matter halos. By the 1990s, the large-scale flows toward the Great Attractor were being mapped. By 2014, Laniakea had been formally identified and named. By 2017, the dipole repeller had been found. The map keeps growing, the motions keep being measured with greater precision, and the journey keeps being revealed in ever more detail. This is what science does at its best. It takes things that seem self-evident, like the stillness of the ground beneath you, and reveals them to be the result of something far more intricate and beautiful than the surface appearance suggested. The stillness is a consequence of motion. The motion is a consequence of gravity. The gravity is a consequence of mass. The mass is a consequence of processes that have been going on since the universe began, distributed across scales from the subatomic to the cosmological, connected by the same fundamental laws from smallest to largest. Science is the practice of following that chain of connection wherever it leads, and it has led here to the extraordinary and verified truth that the ground beneath your feet is racing through the universe at hundreds of kilometers per second while feeling to every biological instrument you possess, like perfect rest. Part 22. Deep Time and the Deep Journey. We have talked a great deal about the present and the near future of Earth's motion through space, but the full depth of the journey also extends backward, into the deep history of the solar system, and even before its formation. Where did the solar system come from? What was the galactic history of the matter that eventually became the Sun, and the planets, and the atoms in your body? The Sun formed approximately 4.6 billion years ago from a molecular cloud in the Milky Way. That molecular cloud was a dense region of gas and dust, enriched by material ejected from stars that had lived and died in the billions of years before the Sun existed. The galaxy was already more than 9 billion years old when the Sun formed. During those 9 billion years, countless generations of stars had burned through their nuclear fuel, exploding as supernovae, seeding the interstellar medium with heavy elements created in their cores and in the violence of their deaths. The atoms in your body, the iron in your blood, the calcium in your bones, the carbon in your DNA, were all made in the nuclear furnaces of stars that died before the solar system existed. They were ejected into the interstellar medium, mixed with hydrogen and helium, formed molecular cloud complexes, collapsed under gravity to form new stars and planetary systems, and eventually, 6 billion years ago, participated in the formation of the solar system from which you are descended. This means that the journey of the atoms in your body through the galaxy predates the formation of the solar system by billions of years. Those atoms have been part of the galactic journey much longer than the solar system has existed. They have been recycled through multiple stellar generations, ejected in supernova blasts, swept through interstellar space, incorporated into molecular clouds, and eventually assembled into a solar system, and then into a biosphere, and then into you. The cosmic journey did not begin 4.6 billion years ago. It began, for the matter that makes up the solar system, with the formation of the Milky Way itself. The galaxy formed roughly 13.6 billion years ago, shortly after the Big Bang. In the early universe, the Milky Way was a chaotic, irregular structure, far less organized than the elegant barred spiral it is today. The first stars formed from pure hydrogen and helium, the only elements abundant in the early universe, and they burned fast and hot before dying in spectacular supernova explosions that seeded the surrounding gas with the first heavy elements. Subsequent generations of stars formed from this enriched material, lived and died, and each generation enriched the galaxy further with heavier and heavier elements. The Sun, formed 4.6 billion years ago from a third-generation or later molecular cloud, is enriched with all the elements necessary for the formation of rocky planets, the chemistry of life, and the construction of conscious observers. The fact that you exist is dependent on 9 billion years of galactic chemistry preceding the formation of the solar system, running through cycles of stellar birth and death, heavy element synthesis, supernova enrichment, and molecular cloud evolution. The solar system's place in the galaxy also affected what kind of star the Sun is and what kinds of planets formed around it. In the early Milky Way, heavy element abundances were lower, and star formation was more chaotic. The outer disk of the galaxy, where the Sun formed, has a particular chemical history, different from the inner disk and from the ancient stellar halo. The specific mix of heavy elements available at the Sun's location when the solar system formed determined, partly, the composition of the planets and the chemistry of life. Looking forward, the deep future of Earth's cosmic journey is governed by the same processes we have described. The Sun will continue its galactic orbit for roughly another 5 billion years before it exhausts its hydrogen fuel and expands into a red giant, engulfing the inner planets, including Earth. Before that happens, the Milky Way will merge with Andromeda in about 4.5 billion years, scrambling the galactic structure and potentially disrupting the Sun's current orbital path. In the merged galaxy, the Sun's orbit will be perturbed, and it may end up on a different trajectory through the resulting elliptical galaxy than the one it currently follows. After the Sun's death as a red giant, the carbon-oxygen white dwarf that remains will continue to orbit whatever structure the galaxy has become by that point, slowly cooling over trillions of years. The heavy elements ejected by the Sun's final death throes will mix into the interstellar medium of the merged galaxy, enriching it for the next generation of stellar and planetary formation. The atoms currently in your body will, eventually, be recycled back into the galactic medium and potentially into future stellar systems. The journey continues, even after any particular arrangement of matter has dissolved. On cosmological timescales, the local group will remain gravitationally bound as the universe expands around it. The merger of the Milky Way and Andromeda will produce a large elliptical galaxy that persists for trillions of years. Other galaxy groups will recede beyond the cosmic horizon as dark energy continues to accelerate the expansion. Eventually, in the far future, measured in tens of trillions of years, even the stars in the merged galaxy will exhaust their fuel, the galaxy will dim, and the remaining compact objects, white dwarfs, neutron stars, and black holes, will slowly decay through quantum mechanical processes on timescales almost too large to comprehend. But the journey, the motion through the universe, will continue until the physics of the universe itself no longer supports organized structure. None of that is coming soon. Earth has roughly 5 billion years of habitability remaining before the Sun's evolution makes the surface uninhabitable. In cosmological terms, life on Earth is young. The journey is far from over, and for as long as it continues, the ground will keep spinning, the planet will keep orbiting, the solar system will keep racing through the Milky Way, and the galaxy will keep streaming toward the great attractor, quietly and continuously. Whether anyone is here to notice or not, every video we make here is an attempt to close the gap between what physics tells us and what it feels like to be alive on a moving planet, in a moving galaxy, in an expanding universe. If this one did some of that work for you, consider leaving a comment and sharing it with someone who would find it interesting. And if you are new, the subscribe button is right there. We would love to have you along for the next one. Thank you for watching. See you next time. Part 23. The Numbers That Make It Real. A complete reference of Earth's cosmic velocities. Throughout this video, we have referenced many specific numbers, speeds, distances, and timescales. It is worth collecting them in one place, not as a dry reference list, but as a way of feeling the magnitude of the journey all at once. Read through these slowly. Let each one register. Earth's circumference at the equator, 40,075 kilometers. Earth's rotational speed at the equator, 1,674 kilometers per hour, or about 465 meters per second, faster than the speed of sound in air, which is 1,235 kilometers per hour. The length of a sidereal day, one complete rotation relative to the stars, 23 hours, 56 minutes, and 4 seconds. The rate at which Earth's rotation is slowing, 1.4 milliseconds per century, imperceptible in a human lifetime, 4 hours of extra day length per billion years. The rate at which the moon is receding from Earth due to tidal friction, 3.8 centimeters per year. The moon is currently 384,400 kilometers away. At this rate, It was about 100,000 kilometers closer when life first appeared on Earth. The amplitude of the Chandler wobble, the irregular variation in Earth's rotation axis position, about 9 meters at the pole. The period of axial precession, the slow wobble of Earth's rotation axis, approximately 25,772 years. The rate at which the axial tilt changes over the obliquity cycle, between 22.1 and 24.5 degrees over approximately 41,000 years. Earth's average orbital speed around the Sun, 29.78 kilometers per second, or 107,208 kilometers per hour. Earth's orbital speed at perihelion, closest approach to the Sun in early January, 30.29 kilometers per second. Earth's orbital speed at aphelion, farthest point from the Sun in early July, 29.29 kilometers per second. The average Earth-Sun distance, 1 astronomical unit, 149,597,870 kilometers, commonly rounded to 150 million kilometers. The perihelion distance, closest Earth-Sun distance, 147,100,000 kilometers. The aphelion distance, farthest Earth-Sun distance, 152,100,000 kilometers. The total orbital path length Earth covers in 1 year, approximately 940 million kilometers. The length of one sidereal year, one complete orbit relative to the distant stars, 365 days, 6 hours, 9 minutes, and 9.76 seconds. The duration of the Northern Hemisphere winter perihelion portion of orbit, approximately 89 days. The duration of the Northern Hemisphere summer aphelion portion of orbit, approximately 93 days. The eccentricity cycle of Earth's orbit under planetary perturbations, approximately 100,000 years, varying from near-circular to noticeably elliptical. The Sun's orbital speed around the center of the Milky Way, approximately 230 kilometers per second, or 828,000 kilometers per hour. The Sun's distance from the galactic center, approximately 26,000 light-years, or about 246 quadrillion kilometers. The time for one complete galactic orbit, 1 galactic year, approximately 225 to 250 million Earth years. The number of galactic years the solar system has completed since its formation, approximately 20. The amplitude of the solar system's vertical oscillation through the galactic disk, approximately 250 to 300 light-years above and below the galactic midplane. The period of the solar system's vertical galactic oscillation, midplane to midplane, approximately 30 to 35 million years. The current height of the solar system above the galactic midplane, approximately 30 to 100 light-years above it. The speed of the local group relative to the CMB, approximately 630 kilometers per second. The direction of this motion, roughly toward the constellation Centaurus, in the direction of the Great Attractor and Shapley supercluster. The distance to the Great Attractor, approximately 150 to 250 million light-years. The estimated total mass of the Great Attractor region, approximately 10 quadrillion solar masses. The distance to the Andromeda galaxy, approximately 2.5 million light-years. The current approach speed of the Milky Way and Andromeda, approximately 110 kilometers per second in the radial direction. The estimated time until the Milky Way-Andromeda collision, approximately 4.5 billion years. The span of the Laniakea supercluster, approximately 520 million light-years. The estimated mass of the Laniakea supercluster, approximately 100 million billion solar masses. The distance to the Shapley supercluster, approximately 650 million light-years. The speed of light, 299,792 kilometers per second. Earth's total velocity relative to the CMB rest frame, approximate, varies with orbital phase, 350 to 700 kilometers per second. At 500 kilometers per second, the distance Earth travels through the universe in 1 second, 500 kilometers. At 500 kilometers per second, the distance Earth travels through the universe in 1 hour, 1.8 million kilometers. At 500 kilometers per second, the distance Earth travels through the universe in 1 year, approximately 15.8 billion kilometers. The age of the universe, approximately 13.8 billion years. The age of the solar system, approximately 4.6 billion years. The observable universe radius, approximately 46 billion light-years. The estimated total number of galaxies in the observable universe, approximately 2 trillion. These numbers are not decorations. They are the actual, measured, verified parameters of Earth's journey through the cosmos. Every one of them was determined by human beings using instruments built on this moving planet, working with light that has traveled across these enormous scales to reach us. The fact that we know them is as remarkable as the journey itself. Part 24. The stillness at the end. We have covered an enormous amount of ground in this video, all without moving from wherever you are sitting or lying right now. The journey through Earth's cosmic motion has taken us from the gentle spin of a planet to the flow of superclusters, through the expanding universe, through dark matter and dark energy, through ice ages and extinction events, through stellar encounters and galactic chemistry, through special relativity and the deep philosophy of reference frames. What remains, now that all the layers have been revealed, is a particular quality of attention. Not anxiety about the motion, not vertigo about the scale, but something more like wonder at the precision and persistence of it all. The fact that everything is moving is not a source of instability. The motion is the stability. The Earth's orbit is stable precisely because it is moving at exactly the right speed for the Sun's gravity to hold it in a closed path. The galactic orbit is sustained precisely because the Sun's velocity exactly balances the combined gravitational pull of the galaxy's distributed mass. Every layer of motion is a gravitational balance, a physics equation solved in real time by billions of years of orbital mechanics. The universe is not chaotic in its motion. It is organized. The large-scale structure of the cosmic web, the filaments and voids and superclusters, reflects the initial quantum fluctuations of the Big Bang, amplified by 13.8 billion years of gravitational evolution into the architecture of galaxy clusters and cosmic flows that we observe today. The motion of Earth through this structure is, from one perspective, determined, the result of forces and initial conditions set billions of years ago, playing out through time with the precision that only physics can deliver. From another perspective, the journey is open. The future trajectory of the solar system through the galaxy, while calculable in principle, depends on every gravitational perturbation the solar system encounters along the way. Every close stellar encounter, every molecular cloud passage, every nudge from the galactic tidal field. It cannot be calculated perfectly to arbitrary precision because the initial conditions cannot be known to arbitrary precision. In a universe governed by quantum mechanics at the smallest scales, and by the sensitive dependence on initial conditions that characterizes complex dynamical systems at larger scales, the precise future trajectory is genuinely uncertain in a deep sense. The journey continues, but exactly where it goes, in the fine details, has not been fully written. You are part of that ongoing journey, not as a passive passenger, not as a helpless piece of matter being carried by forces too large to comprehend, but as a complex, self-aware configuration of matter that has somehow, improbably, found itself able to understand the journey it is on. That understanding does not change the physics. It does not alter the trajectory, but it changes what the journey means, at least to us, at least from here. The ground is spinning. The planet is orbiting. The solar system is racing through the galaxy. The galaxy is flowing toward the great attractor. The universe is expanding around all of it. And you, right here, right now, wherever and whenever you are watching this, you know. That might be the most remarkable thing in this entire story. If you made it all the way here, genuinely thank you. This kind of video takes a long time to research and write, and knowing that someone watched it in full is the reason to keep making them. If you have a question, a thought, a correction, or just want to say where you are in the world, drop it in the comments. Subscribe if you have not. Share this if you think someone else would appreciate it, and we will see you in the next one. Until then, keep looking up. A final word on what this all means. The most honest thing that can be said after all of this is that motion is not just a feature of the universe. It is the fundamental state of everything in it. From the smallest particles to the largest superclusters, nothing in the observable universe is truly at rest. The concept of rest, of absolute stillness, turns out to be an artifact of limited perspective. Zoom out far enough from any apparently still object, and it is in motion. Zoom out far enough from any moving object, and the motion becomes part of a larger stillness, defined by the shared frame of everything around it. This is not a discouraging conclusion. It is a liberating one. It means that the question of whether something is moving or at rest is not a question about the thing itself, but about the relationship between that thing and its context. Change the context, and the answer changes. The universe does not have a fixed backdrop against which absolute motions can be defined. It has relationships, and those relationships are dynamic, evolving, and always defined relative to something. Earth's motion through space is the story of those relationships, played out across every scale, from the daily rotation that gives us the rhythm of a day to the cosmic flow that connects our galaxy to the largest structures in the observable universe. It is a story with no single telling, because every reference frame tells it differently, and all of those tellings are equally valid descriptions of the same physical reality. The one thread that runs through all of them is that the journey is ongoing, that it has been ongoing for longer than life has existed on this planet, and that it will continue long after any current form of life has ended. The ground is moving. The sky is moving. Everything is moving, and here we are, on this spinning rock, somehow equipped to know it. That is everything.